Okay, my dear students, welcome back. Here we are in the course on environmental bioethics in the program of bioethics at St. Thomas University. Beginning always with a little prayer in the name of the Father, the Son, and the Holy Spirit. O Lord, send forth your Spirit, and we shall be recreated. You shall renew the face of the earth. Amen. Father, Son, Holy Spirit. Okay, first off, any questions or comments from previous lectures or anything in the program? Okay, I sent an email. I think I sent an email asking for your internship hours to see where you're at this point. Can anyone confirm they received that email?
I did get it. I'm working on getting it ready for you.
Okay, good. So if one got it, hopefully all got it. And for the four new students, we'll talk about internship probably next Saturday. We can all gather here. There's a football game going on, so these young athletes are all involved in the football game. All right, so let's see. So far, we have been really setting up a little bit our understanding with regards to planet Earth, matter and energy, because we want to look at eventually the bioethical issues in the environment, all right? And we notice that we humans are the only species that can significantly impact the environment for better or for worse, especially nature, the living organisms on planet Earth. Okay, we are unique in having that spectacular capacity, and a lot of it is due to technology, which really puts us way out in a different league or category for all the other species on Earth. We don't see any other species developing the technology that we have by any stretch of the imagination, okay? And that technology is a tool which can be either for good or for evil, right? That's the human factor there. For example, splitting the atom, we know from Einstein's formula, E equal mc squared, that matter contains a lot of energy, right? A little matter contains a lot of energy, and therefore splitting the atom, as it was called back in almost not quite a century ago, but in the 1940s, 1950s, nuclear research, that splitting of the atom can either provide electricity for an entire city or obliterate the city from the face of the earth, right? So it's all how we use it. Okay, Sarah, morning. Turn off the lights here. Classroom 4. Hope that's okay. See? All right, so with this capacity for technology, we have to make the ethical analysis, how we use it, Tony. And also bioethics always has the two-step process of looking at the facts of bio or nature, life, and then the ethics, which is the analysis based on the facts, right? That's also what we call an objective ethics, that we can analyze the situation according to what nature tells us. So to be as objective as possible. All right, so far we've looked at three major aspects of the Earth itself, as a geosphere, right? The matter, and what we see there is these tectonic plates that are slipping. Well, first of all, the three main layers of the Earth, materially speaking, the core, the mantle, and the crust. And the crust is a good enough insulator, even though it's only a few 100 kilometers thick, to insulate us from white hot core in the thousands of degrees centigrade to a temperature range that allows for liquid water on the surface of the Earth, and therefore allow for the possibility of organic life as we know it, which is water-based. Because water, because of the characteristics that we saw last lecture, is so benevolent, right? This coating, this magnetic, this little molecule, magnetic molecule, that allows for chemical reactions, what we call metabolism. We're going to get more and more into that as we go deeper into the course. So first the geosphere, and then the atmosphere. We went from solid to gas, basically. The atmosphere and all those properties. One main property there for maintaining life is filtering out UV and also allowing enough sunlight to part of it be transformed into heat when it hits the surface of the Earth, right? Contributing to that benevolent temperature. So it's a combination of temperature from within the Earth and temperature from without by way of transfer. While I'm on that topic, I also want to remind you of the difference between matter and energy in the sense of cycling and non-cycling. In other words, that matter tends to get cycled in nature, on Earth, and in the universe, whereas energy tends to flow, not cycle, but flow, okay? And so the flow involves transformation of energy, and we talk about transformation. And because we live in a material world, and I don't mean this financially, but I mean, existentially, we live in a material world and our bodies are made up of matter and so forth. We tend to be more attuned to matter than energy, right? And energy is kind of fuzzy generally in our minds and just one big clump. But energy is also very distinct, just as matter is distinct. In fact, energy, in a sense, is even more distinct because all matter, you can distill it down to molecules and molecules to atoms and atoms to elements. So we have the periodic table of the elements, right? Which are all the elements that have been discovered in the universe so far. And it's also very mathematical, by the way, very arithmetical, the issue of elements. It comes down to the proton, right? The number of protons just in absolute numbers, linear, 1, 2, 3, 4, 5, right? What we call the natural numbers, the real numbers make up for different elements. So if there's a single proton, it's hydrogen. If there's 2 protons in the nucleus, then that's helium, 3 protons, lithium, et cetera, et cetera. And it's just, you cannot have, as far as we know, we haven't seen it in nature anyway, half a proton or a fraction of a proton, right? It's a unit by itself, but it becomes stable in the atom. So it's interesting that matter really can be distilled down to elements, whatever element that is on the periodic table, from 1 proton to hundreds of protons on the nucleus. Whereas energy, there are different types of energy. And I'm not talking about kinetic or potential. I'm talking rather about light energy, for example, or heat energy, or electromagnetism, or ultraviolet, right? Or X-rays, etc. Typically, they're waves, but they also have, particularly for light, they can be a particle depending on where it is on the spectrum of frequency. So different types of energies, and energies can transform one to the other, except when we get to heat. When we get to heat is kind of a dead end. In fact, I say not a week goes by without a bioethical issue arising on the horizon. And typically, I've mentioned before, I read the BBC headlines early in the morning just to see what happened overnight in our world. It's very hard. I find it very hard to get international news here in the United States. So I just, on my phone, I go on the BBC for free headlines, and That's the British Broadcast Corporation, right? It's and they have international news. They also have one section there on science, and you can also drill into countries and so forth, or continents if you're interested or have the time. Anyway, there was one article talking about the quandary of time and heat. Interesting, because all of these formulas in physics work either way, either going forward or going backwards in time, including the ones that apply to energy or the equivalencies, like the famous E = mc squared, except for heat. Heat, the formulas that speak of heat in physics can only go forward in time. So we cannot reverse heat to cold without adding energy to the system. But going from, so basically what I'm trying to say is the whole issue of entropy and the dissipation of heat, which is passive, doesn't require energy, rather it's a dissipation of energy. All right, so different types of energies, but the typical one is light, is transformed into heat. Well, chemical energy is another one, like the chemical bond. We'll look at that today in various aspects. Think of glucose and cellular metabolism, cellular respiration, burning glucose or burning wood. We're breaking chemical bonds there, and there's a release of heat, right? And that heat dissipates into the atmosphere and through the atmosphere into the universe. And there's no way of recovering that back passively without adding energy, typically a lot of energy, other energy, to return or to trap heat back into another source of energy. Okay, and so heat entropy goes only one way, and it's forward on the clock. It's a philosophical thing, there's nothing we can do about it, but that's what it is. Anyway, just to make you aware that whereas matter tends to cycle, okay, energy typically doesn't cycle, but rather is transformed. Now, energy could be cycled, if you will, when it gets trapped into matter. For example, wood, right? And we'll look at that process in the redox reaction, the complementarity between photosynthesis and cellular respiration. Energy gets trapped in there temporarily in the carbon-carbon bond, all right, as chemical potential energy. But at some point it's released, typically into heat. And then that dissipates and is lost. And so it's a gradual increase in entropy, which is energy unavailable for work throughout the whole universe. A little tiny planet Earth is one of the contributors for that, okay, for that entropy. All right, so in a sense, we can say, just kind of musing philosophically, that what is running the clock in the universe, the 13.5 or 13.8 billion years of time that we have so far. Remember, I mentioned that the Big Bang, according to the best estimates, occurred about 13.8, let's round it off to 14 billion years ago. So we cannot talk about 15 billion years ago, because 15 billion years ago did not exist, right? Philosophically, we can only talk about up to 14 billion years ago. And so who's running the clock? We can say that heat is running the clock because it's the only thing that is actually increasing with that time, inexorably, without going back, as far as we can tell. All right, back to a little more humble thing here, which is the cycles that we're going to see in nature, and 4 major cycles. So the first part of today's lecture is natural cycles, especially the 4 big ones: water, carbon / carbon dioxide, then oxygen and nitrogen, and several other cycles which are also vital, but not as obvious to us, okay? But still vital because they keep us alive. Phosphorus, sulfur, etc. And then in the context of recycling and the hope of recycling, right? Human-made trash, because we're the only species that makes trash. And that'll be the second part of the lecture. All right, I also wanted to point out a little bit what I'm using here at the beginning of the lecture. Some of us in this course are old enough to remember the four elemental things that kept the world alive in pre-scientific times. I'm going back not hundreds, but thousands of years, okay? I'm going back to classical Greece and even before then, several centuries before the time of Christ. So that's beyond 2,000 years ago, maybe as far as 3,000 years ago. There were four main elements, but so the word element, again, is not univocal, right? Univocal means that it has a single meaning, right? For example, our names are univocal in the sense that it applies to each one of us and only us, right? Our proper noun of our names. But many words are not univocal. They have several meanings depending on the context. So in the context of chemistry, when I talk about elements, I'm talking about the elements in the periodic table, the number of protons that are in the nucleus, right? But also the elements or elemental matter in pre-scientific time were four. Anyone remember? I'll give you a hint. Earth or soil. I'll give you another hint. Wind or air. A third hint. Water. Now the most powerful one. Come on, at least you can tell me the most powerful one. That has power to destroy or to maintain life on Earth.
I think it's fire.
Yes.
Fire?
Naturally, exactly, naturally, right? So earth, wind, fire, and what? And water. In fact, there was, wasn't there a band called Earth, Wind, and Fire? Yeah, what they miss? The water. They were dehydrated. That's a dehydrated band. Right, okay. So you notice the intuition of humans, even primitive humans, how at the macroscopic scale, that's definitely macroscopic, right? In the sense that of the three universes, it's the middle Earth, the middle universe that we can see with our natural senses. We can perceive water, earth, fire, and wind, right? Well, look at here, water cycle, carbon and carbon dioxide, fire, right? Oxygen, the air that we breathe. And there's, I don't know if it's the same band that has that song, sometime all that I need is the air that I breathe. Remember that song? No? Some of us, you don't remember that song? Some of us in the classroom, they remember that song from last century. Okay. All that I need is the air that I breathe. And that's very true, right? Okay. And then nitrogen is the earth. The nitrogen cycle, nitrogen bacteria, denitrogen bacteria that makes the plants grow and so forth. Okay, so really those four elements are here in these four major cycles of Earth, of matter, that keeps life, maintains life on Earth. Okay, so enough musing. Let's go forward into some level of detail here, looking at water first. So the water cycle in nature, again, for the scientists in the group, I apologize because it's going to be a little elemental, but the non-scientists, I hope, will appreciate this because it will bring you up to speed on some basic science, what we would call ecology or earth science or environmental science, okay? We can start with the ocean since we left off with water last lecture, and looking at that surface tension, how it requires about 4 joules of heat to break that surface tension and to release liquid water into vapor, right? To go into the gaseous state without having to boil it, because we're not going to boil the oceans. Plus, boiling the ocean would require more than 100 degrees centigrade. Why? The difference between, why do we add, actually less. I take it back, it's backwards. When we're cooking pasta, right, when we're gonna boil pasta, why do we add a little salt to the water? To lower the boiling point, actually to lower the boiling point. So it doesn't have to reach 100 degrees centigrade. It can be a little lower. I don't know exactly what it is, but it does. Impurities, especially minerals in the water, lower the boiling point of water. I don't know why. It has to do, who knows? But I'm sure physicists and chemists know why. But anyway, it's still close to maybe in the 90s centigrade, you know, and the ocean is not going to get that hot. But there is some release evaporation that occurs at the surface of the ocean of water molecules. And again, I want to emphasize what evaporates from the surface of the ocean, the water that evaporates is essentially water molecules. So fairly close to distilled water, just pure H2O. In other words, the salt doesn't leave the ocean when ocean water evaporates. It's just the water itself, the water molecule that breaks through that surface tension and is released into the atmosphere. At the same time, there's also some water molecules that break into the surface tension and come in, but more is released than absorbed, let's say, at the surface, okay? And that's also why the Dead Sea is getting saltier and saltier. Right now, it's about 10 times saltier than the average PPT, remember, parts per thousand of the ocean water. What's the average PPT of salt water, of ocean water? For those of you who have saltwater aquariums, remember the hygrometer, you have to keep it at 35 PPT, right? 35 parts per thousand. That's average salinity for the oceans. And the Dead Sea is about 300 and something, 330, 340. So it's about 10 times saltier. And it's actually viscous. It feels like baby oil. You can float very high without getting your top part wet and so forth. The reason for that is because it has no outlet and it only has that little trickle from the Jordan River, which on top of that, I told you that the Israelis had already identified from Mount Hermon atop in the Sea of Galilee, what were the underwater springs that were fresh water, the other ones that were more mineral, salty water, and they channeled those salty springs on the side away from the Sea of Galilee to keep the Sea of Galilee fresh, right? Because that's their main source of water for all of the state of Israel. And it's a strategic thing. That's also why in part they went into the Golan Heights and that 6-day war, whatever it was, because that's where the springs are from Mount Hermon, which I think has permanent snow like this, you know, so there's always melt of water into the rock and out the springs. Anyway, so there's no outlet and the inlet of the Dead Sea is already salty, so it increases and there's evaporation. That's also because it's very dry there and there's natural evaporation. And all that evaporation over the millennia is just essentially H2O, pure H2O that leaves. There will be some salt that leaves also, and that's what we call, in Spanish, we call it salitre. I don't know if there's a word in English for salitre. Someone may look it up in the meantime, if bilinguals, if you can look up salitre for English. But basically, if one is at the shore or if one has construction at the shoreline of any ocean, you're going to start getting a little film, a little white film accumulating on the structure that is facing the ocean, right? Because that's just salt that is being picked up. There are salt crystals, minerals that are being picked up by the wind on the surface of the ocean and being swept to the shore, all right? So corrosion is a big factor in construction on the shoreline. And that's why typically you want to avoid, especially iron construction on the shoreline, because it's going to corrode away faster due to that little bit of salt mineral that gets swept off the surface of the ocean by wind, all right? But that's different from the water that is evaporating. It's not in the water itself necessarily, okay? Maybe some, like ocean spray will have some salt on it and gets splattered onto the shoreline and whatever construction is there. Your message, salitre in English, Saltpeter. Okay, thanks, saltpeter. Oh, okay. Thank you. Right, so evaporation at the surface of the ocean, quite a bit, because keep in mind, 3/4 of the surface of the earth is ocean, right? And eventually when that gets to a certain height, typically at the top of the troposphere, which is about what? 10 kilometers, right? It starts condensing because cooling, and remember, so evaporation is water in what state? Evaporation is water in what state? Gas.
Gas.
Exactly. And with cool, so the gas laws, if we add cold to a gas, the gas will start compressing, right? Compressing is equivalent to adding pressure. And so the gas, just like with heat, gas expands. Well, the opposite with cold, gas compresses. So as it gets colder up in the upper stratosphere, or the stratosphere, troposphere, it condenses into clouds. So clouds are really, we're looking at clouds right now outside the window here, white clouds above us, is essentially water gas that is beginning to condense, and at some point it's going to precipitate, but it needs a, so it's like super dense, super dense water gas that needs some kind of impurity in it as a nucleus on which the water droplets start condensing and sticking. Exactly, the molecular magnet thing. They need a little impurity, and those are just particles, dust particles that are floating around. And when enough water molecules attach to this impurity, and when some molecules attach, some water molecules, they will attract other water molecules to attach also because of the magnetic thing. Eventually that gets dense enough to be pulled by gravity. Gravity is a weak force. As we know, 9.8 meters per second square at the surface of the earth. Approximately, you can round it up to 10 meters per second square. That was Newton's contribution. But then going up into the stratosphere, as we go further from the core, what is the center of gravity of any object? Is the center of the object, right? And so of the earth, it's the center of the earth. It would be like the center of the inner core. So as you move away from that center radially, then that gravitational force gets weaker and weaker. So it's a little weaker out there, but still some gravitational force, and eventually makes the rain come down, which we call precipitation. In the meantime, there's also that motion of the winds, and here we add in the Hadley cells and all the weather pattern, the combination of convection plus Coriolis, right? So going up is also convection. Here, remember that gas is also a fluid, so the water vapor going up is convection. As it rises, it cools, and then as it comes down, it warms up. But the atmosphere is influenced by the two forces, which are generally perpendicular to each other. Convection, which is going to be vertical in general, right? Think of the little video we saw. Whereas Coriolis is going to be horizontal because of the rotation of the earth, which translates into something horizontal at the surface, right? Locally. So the combination between those two, the vector that you get out of that, is the wind pattern that generally pushes clouds onto the surface of the earth. And the surface also tends to be warmer or cooler depending on where it is geographically, right? Near the tropics, it's going to be warmer. Near the poles, it's going to be cooler. So the net result of all that is that at some point precipitation happens, which otherwise we call as rain, right? So that's one cycle there. Then the precipitation will go into either lakes or rivers or runoff or underground to form the water table. So we could look at that cycle, infiltration through the layers of sediment and soil and so forth, until it goes down to the water table or the aquifer. There's also percolation, just technical terms like that, has a general flow, again, following the path of least resistance out to the ocean. So there's water, fresh water, generally fresh water that is returning to the ocean, either by surface flow at the delta of rivers, for example, or estuaries, or underground, under the surface, right, by groundwater, also running back to the oceans. We have the example perfectly down here in South Florida, the aquifer, the Biscayne aquifer, which basically is underneath the Everglades and the whole southern tip of the peninsula, anything from Lake Okeechobee south, and basically kind of the whole bottom half of the peninsula of Florida has a lot of water underneath, underground water that is generally flowing. It's fresh water that is flowing out to the oceans, either to the Atlantic or to the Gulf of Mexico. And it's essential that we keep that positive flow out of fresh water into the ocean, right? It's called the Biscayne aquifer. And because when that flow reverses, if we stop, for example, with urbanicity is one big challenge. We need water to live, right? So we use up water, but then our water generally ends up in the sewer, and the sewer is channeled out to the ocean, but not through the groundwater generally. And what happens is the aquifer loses water pressure, outward water pressure, all right? You can think about this in your mind's eye. So if the Biscayne aquifer at some point reverses its flow so that there's more pressure of salt water coming in, what's going to happen, that salt water is going to contaminate the freshwater aquifer, fill it with salt water, make it brackish, and at some point, we're going to start getting brackish water through the tap, which would be horrendous, disastrous, and a real disaster for urbanicity, for living, for human life on the peninsula, okay? And yet what is the flow of humans in Florida, especially South Florida, is inward. It's not, people are not leaving South Florida, people are coming into South Florida literally by the hundreds every day, okay? And so that increases in impact, stress on the Biscayne aquifer and the groundwater as a water source for urbanicity beyond what is already being used for agriculture. Okay, so these are things to keep in mind with regards to the water cycle and human consumption. Challenges with regards to water. That's why I pointed out the document of Water Source of Life, Aqua Fons Vitae, because it addresses these issues, the complexity of these issues. That's on the terrain, on the more or less flat terrain, but we can also go up towards the mountains, and when where the clouds essentially reach mountains, there's another phenomenon that happens there, a couple of things. Generally, air goes up the mountain, depending on how it's flowing, but air goes up the mountain. As the air goes up the mountain, this is something that happens, for example, on the west coast of the US, the real west coast, out in California, Oregon, and Washington State, not our west coast here of Florida, okay? You have the Rocky Mountains there, which have snow caps, so they go up to 10, 12,000 feet high. When that air goes up and it's humid, moist air, it goes up, it starts cooling, right? So condensing, and then the rain happens generally on the western side of the Rockies and flows down the rivers, and that's why that coast is so fertile, and you have Napa Valley and all the wineries and all that, because they get plenty of rain flowing down on the west coast, on the west side of the Rocky Mountains. And so when that wind goes up and cools, there is condensation and precipitation. Some of that precipitation will also be snow. So the snow will be snow deposition on the peaks, on the snow-capped peaks. But little by little, that ice, then that snow ice is compressed and keeps flowing down until it starts melting into the little rivers that will eventually, or little streams that will eventually become river down the mountain. Then when the wind goes over the Rockies and into the Great Plains, into flowing eastward, that wind is now dry. It's now dry. And so the Great Plains generally get a dry wind, and that's why it's more dry on the east side of the Rockies, all right, all along Colorado and all that, all the other states that are there is dry because the mountain range serve essentially as a comb, as a humidity comb to comb out the humidity from the moist air, okay? And that general flow is from west to east in the northern hemisphere of the wind patterns of the Hadley cells. But when you go south to in the southern hemisphere, we have an equivalent mountain range down there, the Andes. And in the Andes is the reverse, because the wind is coming, the moist wind is coming from the east, from the South Atlantic, right? From the South Atlantic, and it's moving through that whole plain of the Amazon Valley. And then it goes up the Andes from the east side and flows down into the Pacific on the west side of the Andes, right? The Andes mountain range. And that's why all the water is filtered out, all the humidity is filtered out on the east side of the Andes, on the right-hand side. And that's what makes for the Amazon basin, which is one of the big two lungs of the earth. The other one being the Congo basin, this tropical rainforest, right? Lush jungle that is very wet. And they have the equivalent of something that we have here, the Everglades, which is a swampy type of water flows over the land and is very, very wet on the Amazon basin east of the Andes. Whereas on the west side of the Andes is very dry, extremely dry. It's a desert that is called Atacama Desert. The whole coast of Peru and Ecuador and all that, all the way down to Chile, extremely dry. Remember one time being in Santiago, the capital of Chile, way down in South America, it hadn't rained there for 3 years. You can imagine all the dust that was around. Okay, and that was typical. That was a normal season for them. Okay, another phenomenon I want to mention here just before getting off this slide is this sublimation. Sublimation is an interesting phenomenon that happens especially in high altitude with snow and ice. And it is basically water going from solid to gas, skipping the liquid phase, all right? It's an interesting phenomenon. It's called sublimation. Sublimation. Again, it's a word that is not univocal in climatological context. It has this meaning. In other sciences like psychology, it has a different meaning. But sublimation is when you have snow that is at very high altitude, in other words, low pressure. And with low pressure, some water in the snow or the ice goes directly into gas and goes into the atmosphere, all right? So some of those, that has also a natural impact because some of those glaciers and some of those snow-capped mountains are losing water in addition to runoff at the base of the ice cap. Also within the ice cap itself and the snow on top of it, by sublimation, gradually is lost because of the thin atmosphere up there, less pressure. And so that is a natural phenomenon, okay? But that's the water cycle. As you can see, obviously the liquid form is the one that is most useful to us for maintaining life in general, plants, animals, etc. Let me move on. Want to look at the carbon cycle, all right? Now, before getting into the carbon cycle, we need to understand briefly a formula here, or recall the formula for the scientists in the room, that we have two complementary reactions, which are photosynthesis and cell respiration, cellular respiration. They're complementary because they use the initial elements or the initial matter of one reaction is going to be the product of the other reaction. And there's a back and forth going here between these four substances, okay? So for example, we can start with photosynthesis. And photosynthesis uses as starting material CO2, which is in the form of gas, right? In the atmosphere, that 0.04%, very tiny percentage, 0.04% CO2 in the atmosphere. And water in the form of liquid water from the soil coming in through the roots, right? So the CO2 comes into the plant, not through the roots because it's a gas. It comes in through the leaves. And the water comes into the plant through the roots because it's liquid water in the soil. Okay, remember this all this liquid water down here. Okay, so those are the starting substances for photosynthesis. Photosynthesis, to me, frankly, is short of magic. It's amazing because it takes light energy and through a chemical reaction that has basically two phases, the light reaction and the dark reaction, et cetera, et cetera. Don't worry about the details, but basically the organelle inside the cell. Remember organelles from way back, right? Organelles are little structures inside the cell that have particular function. So the chloroplast is in the cell of plants, and some bacteria, the photosynthetic bacteria, that take in these two substances, CO2 and water, and combine them through a series of chemical reactions. It's a chain of chemical reactions. The end product is glucose and then oxygen, diatomic oxygen, right? Two oxygens happily together, that stabilizes the molecule. Now, glucose is solid, liquid, or gas? That's a real question. Glucose, is it solid, liquid, or gas? Come on, folks. Sugar. Is sugar
Solid
in the
liquid.
atmosphere?
Is it,
Solid. No, you don't pour.
It
Do
is-
you pour
it
your
is
sugar?
solid?
Yes, solid. You don't pour your sugar into your coffee, right? Okay, so sugar, glucose is solid. How about atomic oxygen? Gas.
Gas.
Right. It's the gas that we breathe. Sometimes all that I need is the air that I breathe. That's the oxygen that we breathe. All right. So the plants are doing this. Plants are doing this all the time during the day because they need light. Okay. During the day. And the cyanobacteria. All right. So you see, plants start with water and CO2, and they form these molecules. They break them apart and restructure them like a Lego thing. And the end result is glucose that gets stored in the plant. The plant doesn't exude, doesn't ooze out sugar, right? Like we ooze out sweat. No, the sugar stays in the plant, right? And the CO2 is released by the plant. As far as the plant is concerned, the CO2, the oxygen is a waste product. Just think about that. Consider that for plants and cyanobacteria, oxygen that keeps us alive and keeps all the animals alive, and the fungi also, by the way, is a waste product of photosynthesis. It's amazing. You know, the complementarity of this
It's incredible that a waste product is needed for life.
is vital. Yes. Conversely, for cellular respiration, when we burn the glucose, right, in the mitochondrion, which is the organelle inside our cells, right, that burns glucose, literally, it's a controlled burning. Using oxygen, we release water and CO2. And in the process, what we're interested in is not the matter, but the energy, chemical energy. So between these two reactions, we have an energy flow, say from light energy to chemical energy. So there's an energy transformation. And the temporary holding of this energy is the glucose molecule, is the carbohydrates. And that's the carbs. That's the high energy in the carbs. It's chemical energy specifically on the backbone of the glucose molecule, the carbon-carbon bond. That covalent carbon-carbon bond is a high energy bond. It's a chemical bond, all right? So it's equivalent to a little tiny battery that is holding that energy, all right? And so the mitochondria, what the mitochondria does, we say it recharges ATPs, So let me go there for a moment. Anyway, so this is a complementary, just two reactions. Two of them, you can think of the gazillion chemical reactions that occur on Earth. Of all those, only two are necessary to maintain life. You know, and they're complementary. It's just amazing. It's bewildering. The elegance, again, we use that word, which we use it very sparingly. The elegance of this redox reaction. Redox is because the beginning substances of one is the end product of the other, okay? And they are complementary. That's why the arrows go one way or the other. So with photosynthesis, we're going this way. It's a reduction, right? That's the RE part of the redox. Reduction, it is reduced. CO2 and oxygen are reduced, in other words, and oxygen is taken out. CO2 and water, I'm sorry, I think I said oxygen. CO2 and water are reduced to glucose because they have been deoxidized. They have, the reaction has taken out oxygen, okay? And that's called reduction chemical. So the opposite is adding oxygen to the reaction, and that is an oxidation. Just like if we put iron out into the atmosphere, it will oxidize, right? What's another word for oxidize? Rust. It oxidizes, and it even changes the color just to let us know. So when we add oxygen to a reaction, we are oxidizing. And so we oxidize glucose, burn it back to CO2 is one of the products, and water is another product. And we exhale these two. Now, the water that we exhale, is that liquid water? No.
No, it's gas.
It's the gas water, and it's a byproduct. This is the water that we don't use for drinking because it's gas water. And we hear about CO2, that every animal and fungus releases CO2, but we also release water vapor through our mouth, and we just need to use that on the glasses. See, when it turns opaque, that's water vapor that's coming out of our breath, okay? So we also release water vapor. That's why we need to drink water, because we dehydrate with every breath. All right, so.
But Father, but we also, when we are sweating, we
Yes.
also release water.
Yes.
Liquid
So-
water, I mean.
Yes, exactly. And so we also lose liquid water through sweat, you're right, and it's also part of that reaction. Only that liquid water is not pure. It has impurities in it. It has toxins. It has minerals that we lose, the electrolytes that we lose through sweating. So you're right, but we need to replace that water too, okay? And then the third water is the water of the urine that has even more toxins in it. That's the metabolic process for getting rid of waste of metabolism. Okay, so what happens here is then that the carbon-carbon bond, which I've shown here, all right, is the one that is the high energy bond. And it's a chemical bond. It's a chemical energy. And that recharges these molecules called ATPs. That's as far as the detail that I'm going into, but basically adenosine triphosphate, this is the energy molecule of the cell. In other words, all of the metabolism that occurs in our body uses ATP as a battery source, as an energy source, okay? So these little ATPs are like gazillion little batteries, molecular batteries that we have within each one of our cells to run the metabolism that is needed there, the activation energy for metabolism. What I want to point out that this is pretty obvious for animals and fungi, cellular respiration, because we don't photosynthesize, right? We can go out and suntan all we want, but we're not going to photosynthesize out there in the sun, all right? Because we don't have chloroplasts. What I do want to point out that is not too obvious is that plants also have cellular respiration because plants are also alive. So in addition to chloroplasts, plants in their cells also have mitochondria because they also need to metabolize. In other words, they also need to stay alive, correct? And so part of the glucose that the plant produces will be used by the same plant to stay alive through cellular respiration. So plants also respire. And they respire, of course, at night. They are only respiring, they're not photosynthesizing. So a plant stays alive at night, right? Doesn't die at night and resurrects in the morning when the sun comes out. So a plant stays alive all night long without any photosynthesis. So that's part of the storage. Part of the storage of the glucose in plants is used for maintaining that same plant alive, all right? But it's very tiny compared to the excess glucose that they produce. So they produce an overabundance. So this is kind of the chemical equivalent of the overabundance that we see in nature all the time, okay? The overabundance of everything. There's some mechanism in nature that tends to produce overabundance. But then that overabundance is balanced out by the needs of some other organism. Okay, so the abundance of one organism is the dearth or the need of the other organism to stay alive. When a fish, a single fish, female fish lays out thousands of eggs, you know, and then the male fish lays out millions of sperm to fertilize those thousands of eggs. All that was needed for replacement, what's replacement for one male and one female fish? What's replacement? Two, right? One male and one female baby. That's replacement. And yet we have thousands. So 99.99% of those little tiny fish are going to be eaten by other fish and other creatures to keep them alive. And so the excess of one is the dearth or the need of the other to stay alive. And overall, in the big picture, there's balance. There's balance. And that's also an important argument to know for restoration, because when we are trying to restore an area, the first thing is getting out the invasives and leaving the place as it was originally for nature then to come in and restore itself, especially with the seedbed that is there. All right. So, yeah.
If you have a moment, yeah. I remember you talk about the leaf color change during the autumn, during this season. Talking about photosynthesis, can you please recall a little about the process of the change of the leaf?
Okay.
Very interesting.
Yeah, okay. So what happens there is that we have several different pigments of, right? The fall. That's why it's called fall, because the leaves fall literally from the tree. The more technical term is autumn. Yes, and it was 21 September, no? Was it 21 September or something like that? The official change of the season, the fall equinox, where we had 12 hours of day and 12 hours of night at the equator. All right. Yes. So it turns out that leaves have various different pigments. They have four main pigments: alpha chlorophyll, beta chlorophyll, carotenes, and xanthophyll. So alpha and beta chlorophyll tend to be on the green side. In other words, they absorb everything but green. So they reflect green, and that's why we see the leaves green. And those are the major pigments on leaves, on green leaves. But they are also more sensitive to temperature, and they start dying, decomposing. Alpha and beta chlorophyll start decomposing when it gets cold. But the other two pigments, the carotenes, which are obviously orange, right? And that's what we call carrots That's why carrots are orange, carotene, and xanthophylls, which are even deeper, red and purple. In other words, they absorb on the other end of the spectrum, so they reflect on the light spectrum, orange, red, and purple, and that's why we see them. Those pigments are also there. The carotenes and the xanthophylls are also there when the leaf is green, but they're in a smaller quantity, and therefore we don't see them because it's saturated with alpha and beta chlorophylls, and so we see we cannot see at the molecular level with the plain eye. We can see it under a microscope, but we don't see the carotenes and the xanthophylls until the alpha and beta chlorophylls start dying or decomposing. And then all we see are the other pigments that have been there all the time, but hiding in plain sight. And that's why the leaves turn first orange, then red, then purple. And then when finally it gets cold enough that the carotenes and the xanthophylls also die and decompose, then we just see brown. At that point, we're seeing the fibrous material decomposing, the fiber of the plant itself, mostly the cellulose, decomposing brown, literally burning up. Okay, so it's also an oxidation process that is occurring to the cellulose once they turn brown.
Thank you, Father. Thank you.
All right. People, they call it piping, piping or picking or something like that. Piping, piking. When they go see the people go up in the autumn to see the turning of the leaves, up in the fall up north. All right. So now carbon cycle, with regards to CO2 and the carbon cycle, need to push forward now a little bit. There is contribution of CO2, and then there is sinking of CO2. All right, I'm talking about CO2 itself. So we're getting into the carbon cycle and eventually what we call carbon budget and carbon stock. So major production of CO2, in nature. We can start with the geologic activity, like for example, a volcano, explosive, literally tons, megaton, gigatons of CO2 released into the atmosphere, but those are sporadic here and there. There was much more going on in the early Earth, back a few billion years ago, right? When the plates were still rubbing against each other and so forth, there was much more volcanic activity. All that has quieted down quite a bit, to the point that when a volcano explodes on Earth today, it's a big sensational thing, But if we go back a few billion years ago, it was a daily event and there was no possibility of life. It was just too explosive, literally. But that contributes to the CO2. There's still some of that going on today. The big one is just fires, natural wildfire, which is called combustion in nature, which is not necessarily a bad thing. When they're wildfires, are good. It has a lot of impact on the nature. It clears out the weakest and so on and so forth. And it restores, because then that the ash that is left mixes in with the soil. It forms potash. And that's a very fertile soil actually for new plants to grow, especially conifers, all right, including our pine forest here. Of course, this is an urban forest, so we can afford a wildfire. We pray that we never have a wildfire here from lightning, because we cannot prevent lightning wherever it wants to hit. But combustion is a major production of CO2 today on Earth, naturally, unless it's a man-made fire, a human fire, fire, which are very, very dangerous and disruptive, and even into agricultural and urban areas. Also from cellular respiration, the millions and billions of organisms, plants and animals that are respiring, and also fungi respire, bacteria respire, anything that is alive is respiring, as we just saw, producing CO2. Then, in addition to that, the new one, if you will, just in the past few hundred years, is the human influence, mostly from industrialization. These are the fossil fuel, burning fossil fuel, right? Combustion of fossil fuels, natural gas, coal, petroleum, gasoline, the car that you're driving, etc. But industry, mostly industry, is the big offender here of big time CO2. All right, so that has to be added into the total CO2 produced into the atmosphere on an annual basis. That makes up for that 0.04% that we talked about earlier. Now, on the sinking side of recycling that CO2, of course, the major one is photosynthesis, both on Earth and in the oceans, and also at the surface of the ocean because of phytoplankton. So you can think of phytoplankton a little bit like a lawn that is floating on the upper foot or less, just a few inches of the ocean, right? Of the 75% of the surface of the Earth, of the planet, has these phytoplankton, which are microscopic algae, mostly floating there and photosynthesizing. The phytoplankton is the beginning of the food chain and the food web in the ocean, because then that phytoplankton is being eaten by zooplankton, little microscopic organisms, animals that feed on the phytoplankton, and then little larger organisms will feed on the zooplankton, and you go up the food web all the way up to whales, the largest animals on Earth, okay, in the oceans. So it's a very exciting thing. The phytoplankton absorbs quite a bit of CO2 also. There's also CO2 that is trapped, that is literally coated and dissolved dissolved into water, into rain. And that also sinks. CO2, when that rain with CO2 mixed in it as a gas, right? Just like water also has oxygen in it mixed in as a gas, and it becomes part of the ocean water, and eventually it will dissolve and then be used by plants or even animals, fixated into mostly the bone structure or calcium carbonate, which is a mineral that is used by invertebrates like corals and other microorganisms that fix that carbon into sediments, either by decomposition of the animal or the organism, or that other process that we saw by the parrotfish of eating coral and making sand, right? That's basically calcium carbonate that is sinking to the ocean. Miles, literally miles of sediments accumulated over the eons on the bottom of the ocean. That's all carbon that has been sunk into the Earth, and therefore it's not CO2. It's a good thing. It's a positive thing, right? That's all overall sedimentation. All right, now let's look at the budget, because this now we're going into the ethical analysis, right? The budget, if we exclude humans from the picture for a moment, from this budget, that budget is balanced, you know, there's a net zero. Let's look at the units of this just to have and try to wrap your mind around this number. Gigaton, a gigaton is a billion metric tons, all right? Now, a billion is 10 to the 9, as you can see here. Billion with a B, all right? That's a gigaton. It's a unit, massive, humongous, large unit of measure of weight or mass, actually, mass. All right, so just to get a feel for that, it's a billion metric tons, and 1 metric ton, one of these billion, 1 metric ton is 1,000 kilos. Now, let's convert this to the British, as we are accustomed to. We're not accustomed to the kilo, but we are accustomed to the pound, right? 1 pound. So how many pounds in a kilo? 2.2, so about 2 pounds, 2 pounds per kilo. So 2 pounds, all right? 2 pounds make 1 kilo. Therefore, 1,000 kilos is 2,000 pounds. So a gigaton in pounds is 2,000 billion pounds, all right, of weight, of mass. 2,000 billion pounds of mass. Imagine carrying that from the supermarket home by hand. All right, that's a gigaton. So these numbers are in gigaton. And this is the annual budget in a year's time, in a year's time. So let's start with the green numbers. The green numbers are the numbers of carbon in gigatons. All these numbers are gigatons, all right? That are being sunk by photosynthesis, for example. All right, sorry, green is for land and blue is for ocean. So let's look at land first. 120 gigatons of carbon are sunk by photosynthesis on an annual basis. Plus 3 from human production, okay, industrialization. So that's a total of 23. But at the same time, plants, because plants respire, plants are alive, plants are producing 60 gigatons, right? And the soil is also producing 60 gigatons of respiration, mostly by microbial respiration. And the decomposition is rotting of an animal or a plant that fell on the land, on the forest, and is rotting, is burning away, is combusting, is decomposing. So that's also producing CO2. So you can see that the 60 gigatons of microbial respiration, basically below ground, plus the 60 gigatons of the plants respiring, the plants staying alive, that's above ground. 60 plus 60 is the 120 that photosynthesis is sinking. So there's a net zero there. In other words, nature by itself, we exclude the human. Nature by itself on land has a balanced system. And that is a balanced system that has come to balance over the millions of years of life on Earth, right? So the cellular respiration, 60 plus 60, is balanced out by the 120 of photosynthesis that occurs on land, excluding the human hypothetically, all right, bracketing the human for now. In the oceans, something similar. There is a net of 90 gigatons of CO2 being sunk into the oceans, mostly by the phytoplankton, all right? And some of that, remember, is also dissolved into the rainwater that comes part of the ocean water. So that's 90, but at the same time, there's respiration going on in the ocean, all the animals and the phytoplankton itself that is also alive, that is also respiring. There is a 90 gigaton production of CO2 annually from the oceans. But you can see that it's a washout, right? Pardon the pun, 90 and 90, so 90 of cellular respiration is absorbed by 90 of photosynthesis in the oceans. So that's a net zero. However, and there is this extra 2. So this extra 2 in red is that photosynthesis in the oceans, in addition to the 90, also absorbs 2 extra gigatons of CO2. All right, these are the red numbers. 2 extra gigatons of CO2 from photosynthesis in the ocean. On land, photosynthesis, for some reason, is more effective. Absorbs, no, actually, because it's 120, so it's relational, it's proportional. So 90 to 123, okay? So 3 gigatons of extra CO2 are absorbed in photosynthesis, in addition to the 120, right? So when we add this 3 and this 2, we get 5. It turns out now we're going to drop in, we're going to parachute in the human factor. In other words, industrialization and machinery. This includes the fossil fuels that industry is burning, which is a major contributor to CO2, but also transportation, either private or public transportation throughout the world, which it runs mostly still today on gasoline, right? Fossil fuel burning. And all the other CO2 that is produced by humans, typically through some kind of machinery, but also burning, etc. That is a total of 9 gigatons being produced on Earth today. So 3 plus 2 is 5, that is being sunk. So 9 plus 5, 9 minus 5 leaves a net 4. And this is the 4 that I want to get to. All right. This 4 is a 4 net increase of CO2 annually on the atmosphere by human production, by human technology, human industrialization, human living, because we necessarily need to live by using energy. And that energy is, when you trace it back out, is burning some kind of fossil fuel. So the electricity that we're using in this building right now to keep us cool, to keep us 10 to 15 degrees cooler than the heat outside, is using electricity from FPL, and FPL at some point is burning fossil fuel to generate electricity, to generate the dynamos, the generators, the electric generators, right? So you see, of the 9 gigatons that are produced by industrialization annually, 5 are being sunk by nature, but there's a net 4 excess increase annually. And that's the increase, that's the graph that we saw shooting up, going through the 400 ppt back a few years ago, all right, and shooting up vertically in an exponential fashion. And that's the big concern. That's the big concern. And that's the reason for the annual conventions on the COP conventions. The most famous one, the latest one, was the that happened just before the COVID thing, was the
Climate change.
yeah, climate change, no, but the one in the Paris Accord, the Paris Convention, right, of which we got out of under Trump, and then we got back into under Biden, and so forth, back and forth. But we'll get to that in much greater detail. But this is a concern, the CO2 that is warming. So this is the warming, the global warming, is this increase of CO2, because CO2 holds high heat, is a greenhouse gas, right? Holds onto heat like water does. All right, so that's the concern. I just put it out there for now in numbers. This is the issue. All right.
Father, real
Yep.
quick,
Mhm.
this is what I'll say. So we put into the equation humans,
Yep.
but there are a lot of mammals within around the world,
Yep.
and obviously billions of insects, let's say,
Yeah.
and they also express CO2.
Yes.
So why is the fraction for humans not incorporated into kind of the global CO2 naturally in the equation that you're using primarily plants in the ocean and plants on Earth? I know those are the two biggest exchangers, but there's always been some type of I think CO2 expressing I don't want to say mammal or
Animals in general, and fungi also.
Animals, yes, some type of animal on Earth.
Yeah, and fungi, you know, we don't see too many fungi, but fungi are all over the place. Fungi are on the ground right now, and some of them cover thousands and thousands of square feet under the earth, and they're also respiring, and they're not photosynthesizing. Okay, so they're producing. So yeah, so 2 points. First of all, this graph is simplistic. This diagram is simplistic in that it's only showing plant respiration, but they should take out the plant word here and just put respiration above ground. I would better this graph here by putting above ground respiration and underground respiration on land. All right, so that would include the animals also, and the fungi here. Well, the fungi could be also be on the ground. And then here also, see here they just said respiration. So they did not say phytoplankton respiration, right? They just said respiration. This includes animals, no fungi on Earth, on the oceans that we know of, but plants also, and algae, okay, and bacteria. So overall respiration, natural. So what this really graph is trying to contrast in the numbers and the color of the numbers is the natural numbers of green and blue with the red numbers, which is human, it's excess, right? The one species that has industrialization. And this is technology. This is the downside of technology. We cannot live without technology. We could live without some technology today, but not without all technology, because it's essentially keeping us alive. So yeah, that's why it's simplistic, and it's only saying plant respiration, but this should include also animal and fungi and bacteria respiration. Okay, so that clarifies the inadequacy, if you will, of the graph.
Thank you.
Yeah. All right, let me move forward a little bit, unless there's any other question or comment. All right, oxygen cycle. The oxygen cycle is a little more complicated because oxygen has kind of three options. It can either be by itself, in other words, diatomic, O2, which is what we respire, right? What we breathe in, what we inspire through our lungs, through our alveoli in the lungs. So O2, which is what is picked up by the RBCs, the red blood cells, or it can be in the fashion of water. In other words, this oxygen, part of the water molecule, so there it is trapped into the water, right? Or it could be in the form of CO2. In fact, CO2 has two oxygens and one carbon. So those are the three main options for oxygen elements in nature generally, all right, as far as cycling. So that's why the cycle is a little bit more complicated. Since we were on the CO2 in the previous slide, so let's look at atmospheric CO2 here, water. Now we're looking at, the oxygen component of the CO2. In other words, this oxygen here, the two oxygens that are tied into carbon, that is going to get cycled into photosynthesis, like I was talking about. So that is absorbed, and that oxygen then is broken off, is released. What I want you to focus is on the oxygen cycle. In other words, focus on this oxygen in the CO2 molecule. That oxygen is going to be released through photosynthesis, right? And the carbon is going to be sunk into the glucose molecule, all right? So that oxygen is released through photosynthesis here, right? Those are the black arrows. So that goes into diatomic oxygen, which is also going to mix in with precipitation. So water also oxygenates, either through rain or through the mixing at the surface, the stirring of the surface of the ocean, right, is what oxygenates the water. And it's essential that water, natural water, whether it's ocean or lake or river, be oxygenated. In other words, that it has gas, oxygen mixed in it, dissolved in it, because that's what fish breathe through their gills. Fish breathe water, diatomic water, gas that is dissolved into the water column of either ocean, lakes, or rivers, or wherever the fish is. Okay, and so the gills are kind of the equivalent, equivalent of lungs for fish. And so that oxygen, that atomic oxygen, then gets dissolved into water, into liquid water. At some point, through cellular respiration, that oxygen is burnt up, is taken up, right? And so it's trapped into the CO2. Okay, so cellular respiration takes oxygen and incorporates it to a carbon molecule, and then that's released as gas into the atmosphere. It could be natural by the cellular respiration that we've been talking about for a long time, or decomposition, which is natural burning up of organic material, or back to the burning of fossil fuels, combustion by some kind of machinery. I also want to point out that weathering of rock. So rock also has diatomic oxygen trapped in it, all right? And when that rock weathers or breaks down minerally, it releases oxygen also. Okay, I already talked about the water cycle. So just to keep in mind that oxygen is also trapped in water, in the water cycle, in the water molecule, all right? So oxygen has a more complex cycling, if you will, depending if it's diatomic, if it's within the water molecule, or if it's within the CO2 molecule. Let's move on to the fourth one, which is nitrogen, the nitrogen cycling. And this nitrogen cycling is going to be very much involved in organic material, especially proteins. So very, very briefly, you don't have to give me this level of detail in the summaries by any stretch of the imagination, okay? But I typically go into excess of detail. So here it is, just for the record. Proteins are the major source of nitrogen in nature, or one of the major ones, and it has to do with life because the proteins are the workhorse of the cell, of metabolism. Proteins are, for example, enzymes are proteins. So proteins are either structural or functional or both. And I'll give you an example. Structural proteins, the hair. All the hair is protein, the fingernails, nails are proteins, toenails, so all that is a protein, right? Keratin. There's also structural protein in the cells themselves, in the cell membrane and other parts. But then functionally, they have a huge function. Essentially, life, we could not have life as we know it on Earth without proteins, because the proteins are the ones that catalyze all metabolism, all the chemical reactions by way of enzymes. Okay, so enzymes are proteins. And the structural proteins, they have 4 levels of structure. They're just named primary, secondary, tertiary, and quaternary structure. The primary structure is just the sequence, right, of proteins. But proteins are made up of amino acids. This is where I want to start here with amino acids. There are 20 amino acids in nature, 20 amino acids, and they are the building blocks of proteins. They are the precursors of proteins, all right? And they all have this general structure. They have this carboxyl group here, and then they have what is called an amino group attached to it. And it's the amino group that is standard, which is 1 nitrogen and 2 hydrogens. So it's kind of equivalent to a water molecule in this sense, but it has nitrogen instead of oxygen. All right. So it leaves 1 bond available on the nitrogen for this carboxyl end, and this can change significantly, right? The chain of the carbon, it can be 1, 2, 4, 6, 8, etc. carbons, and the peripherals, what is called the, what are the peripherals called? The, there's a name for it. Anyway, can also change, right? The radicals are the ones that are attached around the sides. Those can change in 20 different conformations naturally in nature, and that's what we call the 20 amino acids, that the 20 natural amino acids. Excuse me, they are the building blocks, and that's basically what we do when we digest. When we digest protein, in other words, once we chew meat or we don't chew it, we gulp it down into the stomach. The stomach, by acidic reaction, by peptidic enzymes, which have a pH of about 1.2 or 2. Doctors, please correct me, the clinicians in the room. What's the pH of the stomach? Around 1.5 or 2, no, more or less. Very acidic. I hear that if you throw an old penny into the stomach, it will come out very, very shiny because it's so acidic.
It's more or less between 1.5 and 3.5. It's very acid. Yes.
And 3.5. So the average of about 2, very acidic. All right. It's like concentrated sulfuric acid that will burn a hole through a table. All right. That's the normal pH, natural normal pH of the stomach. And that's why the reflux, what we call heartburn, has nothing to do with the heart. All right. It's just a little reflux above the pylorus, the top sphincter between the esophagus and the stomach. There's a little circular muscle, soft, smooth muscle that sometimes doesn't close totally tightly, We get a little reflux of that gastric juices flow on top of it, and it burns. It starts digesting the esophagus. Okay, and that's what causes the heartburn, because it's in the general region of the chest, and it is a burning, it's an acid burn, but it has nothing to do with the heart. Okay, anyway.
But in Spanish, you say acidez.
Acidez, sí, acidez estomacal, right, reflujo. All right, so these amino acids get linked together in a chain, right, in a chain. And so it forms, here we have the primary structure, like I mentioned, is just a linear sequence of amino acids, which typically the convention is to abbreviate them into 3 letters, right? So ASN, that is arginine, GLY, glycine, PHE, phenylalanine, GLU, glutamine, ALA, alanine, arginine, etc., aspartic acids, leucine. These are all the 20 amino acids, right? In a, they don't have to be all 20. You can have repeats, any number of combinations, myriads of different combinations on them, but always linear. Okay, always linear, and that's the primary structure. And then that structure, 3-dimensionally, starts coiling upon itself. It actually forms 2 types of 3-dimensional structure, either a coil that is called an alpha helix, or a sheet, right? A sheet which is called a beta sheet. Those are the 2 main 3-dimensional structures beyond the primary structure, which is just a sequence of the amino acids. So that's called the secondary structure. That is necessary but not sufficient to have a functional protein, right? Then these come together into more folding when we have several alpha helixes and several beta sheets coming together in a longer sequence, right, of amino acids. Then they start forming what we call peptides, and then polypeptides, and they start folding upon each other. That's the tertiary structure of different lengths of alpha helices and beta sheets, as you see here, starts getting more and more complex. Finally, several of these complexes of these tertiary structures come together again to form what we call finally the quaternary structure, or the actual functional protein. One example, this is hemoglobin. And hemoglobin is made up of 4 subunits of myoglobins. Okay, so myoglobins are like the tertiary structure, if you will. Individually, independently, they are non-functional. But when you take 4 myoglobins and cluster them together in a particular conformation that is symmetrical, you get the functional hemoglobin, which is at the center of an RBC, right? And that is the functional protein itself. And at the very center of this quaternary structure, which, as you can see, is symmetrical, of these 4 myoglobins, there will be a heme group. A heme group is an iron atom, iron, Fe, all right, which in Greek is known as heme, and in Latin is known as ferrum, and that's why iron is to this day still called ferrum on the periodic table. And that's what's holding these 4 myoglobins together, in addition to their particular conformation. And it is that iron that gets oxidized by a diatomic oxygen, right, molecule to make it FeO2, and that makes for oxidized blood is actually oxygen-rich blood, which goes from the lungs to the tissues of the body for cellular respiration. When that oxygen gets off at the cell, a CO2 is being picked up as a byproduct of that cellular respiration, right? And then now that becomes deoxygenated blood that becomes generally is known as venous blood in the tissue circulation, in the systemic circulation, but not the pulmonary. The pulmonary circulation reverses the artery from the vein. But anyway, going back to the lungs, that CO2 then is released. And it's the iron atom at the core of the hemoglobin molecule complex that achieves respiration for us, from the atmosphere, which is basically outside the lungs, to each tissue, each cell of our body through capillarity, through the circulatory capillarity. So again, talk about elegance. It's just bewildering. All that done by protein. Without the myoglobin, there's no cellular respiration because we cannot come up with a hemoglobin complex. Okay, and that's the quaternary structure, and that's the actual functional protein complex. What happens is that these proteins are being broke down by digestion or by decay into mostly ammonia, and then ammonia is excluded, it's urinated out of the body into the soil, and then bacteria will break it down further into nitrates. And these are, they're known as nitrifying bacteria. They go from nitrites to nitrates. Basically, the nitrates are the ones that are available for the plants to absorb into nutrients, right? I'm thinking of fertilizer when it's added to the plants or in nature by the bacteria. So plants are also very much involved in the protein cycle of nitrogen through absorbing nitrates from the ground, and also they can absorb some nitrogen gas. Remember that N2 is about 2/3 of the atmosphere is nitrogen gas, right? Inert. There are some bacteria that fix nitrogen. They're called nitrogen fixing bacteria. And they take that nitrogen gas from the atmosphere and fix it into the soil for plants to absorb that nitrogen also for their tissue, for producing their tissue. So there's protein in plants. For example, legumes are known for a lot of protein, the beans, right? Beans have a lot of protein in them, and that's vegetable protein. It's not animal protein, and it's very healthy because it doesn't have all the cholesterol that animal tissue, that animal flesh has, in addition to the protein in it. In other words, the nitrogen cycle in nature can either be done by decomposition of animal material, right? Or by fixing nitrogen, atmospheric nitrogen, by nitrogen bacteria. But bacteria are key in this process either way, either nitrifying bacteria or denitrifying bacteria, but they make nitrogen available for plants to integrate into their tissue, all right? And then the consumers eat the plants and integrate it into our tissue, which is mostly flesh, the protein component of our body. Also, okay, well, there's another diagram here, more detail of how the nitrogen cycle works underground by the bacteria. I'm not going to dwell in it, but this is basically underground, the various bacteria as they either nitrify or denitrify the raw material so that it can be absorbed by plants. I'm not going to dwell on that diagram. I want to move forward because I'm running out of time here. Other cycles that occur in nature. First of all, we look at the component of a human body in percentages. Okay, we look at the component, most of our, just by the elements, not by molecules, because by molecules we're mostly water, right? We're about 80–90% water, but by elements. By element, We're about 65% oxygen. We're about 18-20% carbon, 10% hydrogen, about 3% nitrogen, and the rest that is left, if we add all these percentages, is 4% left. Or now, in other words, when we add the four main elements of oxygen, carbon, hydrogen, and nitrogen, what is left is 4%, and that 4% is distributed among all the other elements that are needed in our body, dozens of elements that are needed in our body to maintain metabolism. All right, but they're in small amount, very small amount. For example, phosphorus. In a very tiny amount, phosphorus is necessary for staying alive. Okay. Sulfur is also necessary for staying alive. Then we have a number of minerals. The most important ones are calcium, potassium, sodium, chlorine, magnesium. These five are the main minerals that are needed in the body, but other are also needed for maintaining metabolism. In other words, for all the thousands and thousands of chemical reactions that are occurring in our body every minute. And finally, we come down to the trace elements. Trace elements, which typically are less than 0.1% in our bodies, and sometimes even much smaller than that, all right? Iron, manganese, iodine, copper, chromium, cobalt, silicon, zinc, boron, many others are in our body in the trace amount, but still necessary. The fact that they are in a tiny amount doesn't mean that they are superfluous. They're necessary for maintaining life. And so you can see the bewildering complexity of metabolism. And this is not just a human, it occurs in every organism that is alive, essentially, in different proportions. Okay. We can go from the largest need, if you will, which is going to be oxygen. And then second to that, carbon, hydrogen, and nitrogen. But then also all these other elements in smaller and smaller quantity, but still necessary for maintaining life.
Well, I'm sorry, but I would say they might be very small amounts, but if you are out of magnesium, you will be very sick.
Yes.
And then for pregnancy, iron.
Iron. Exactly.
Wow, this is incredible.
It's very tiny, but essential. All right. So the fact that it's very tiny doesn't mean that we can do without. We may be able to do without for a small period of time, but eventually, you know, we have to pay the piper and we have to get those essential elements back in. All right. Okay. And that's all through dieting, basically. For example, just I get so sidetracked. Iron before Teflon, right? Our natural source of iron, you know what it was? Just a skillet, the frying pan. It was a natural source of iron, and we didn't even realize it. But when our moms were cooking food for us and were scraping the iron skillet, the iron pan with an iron fork or spoon or whatever, they were scraping off molecular iron that was going into the food that we ate. And that was a natural source. And then came Teflon, which coated those old pans, and we lost that source of iron, which was major. So that's just one example. Okay, hydrogen. I need to mention hydrogen. This last thing I'm going to mention problems before the break, okay? Which is this. So hydrogen is also essential. You notice here is the third largest, 10%. It's all over the place because remember, for carbohydrates, we need two molecules, right? We need two elements. For carbohydrates, which is one of the four major group of organic compounds, right? Carbohydrates, proteins, lipids, and nucleic acids. So for carbohydrates, we need hydrogen and carbon. And hydrogen is just all over the place because whatever bond is available will be stabilized by a hydrogen bond, okay? By hydrogen bond. So hydrogen is all over the place in gas and solid, basically. So it's either gas, diatomic hydrogen, H2, nice and stable, or it is trapped into myriads of molecules organic and inorganic in nature, but a lot organic molecules, all right? So any bond that is out there reaching out with a little charge, typically a negative charge, the hydrogen will come and stabilize that charge, all right, and neutralize it with essentially a proton called hydrogen bond. Now, in the atmosphere, where we have the diatomic hydrogen, this is the percentage, okay? So 0.00005%. So decimal, centesimal, millesimal, 10 millesimal, 100 millesimal, 500 millesimal percentage of the atmosphere is hydrogen. And that's a good thing, that we have such little hydrogen in the atmosphere, because it is highly flammable and explosive, all right? Remember the Hindenburg, before we switched to helium, which is inert, the blimps and the airships were made out of hydrogen because it's lighter than air, than the regular air, and it tends to rise. So it keeps things afloat until these are called airships, right? Until this airship got close to a tower and make supposedly some kind of electrical contact and blew up in the middle of the air. And that happened back in the 40s. You can look it up, the explosion of the Hindenburg. And from that point on, they stopped putting hydrogen into balloons, all right? So now it's helium. But hydrogen gas is highly flammable, and that's why it's a good thing that most hydrogen is actually trapped in chemical bonds, in hydrogen bonds, right? Stabilizing molecules all over the place, but significantly carbohydrates. But not just carbohydrates, also proteins, there they are, and lipids and nucleic acids. There's hydrogen all over the place. Okay, you're way overdue for a little break, and so am I. It's 11:15. Any questions or comments on these cycles? Let me just go quickly to the first slide here. As you can see, we're talking about cycles in nature of the four major ones: the water cycle, the carbon and carbon dioxide cycle, oxygen cycle, nitrogen, and then all the other cycles that I added at the very end there for maintaining life. All this necessary for maintaining life on Earth. And these are natural cycles, okay? The big concern for us, of course, is this one here of the CO2 increase, mostly from the past 250 to 300 years of increasing industrialization on Earth. The second half, we're going to get into, which is going to be a short half, obviously, for about an hour. We're going to get into man-made trash and hopeful recycle of our trash, since we are the only species that produces trash that is not naturally cycled in nature.
Father Trophy, I have just one question, and maybe you can answer it later. No,
Yeah.
no. But if it's 4 what's the name? Gigaons, whatever.
Gigabyte, not gigabytes, gigatons. This one.
Yes, gigatons
This is a
per
schema.
year. Per year.
Yep.
We have to add that to 250, like multiply that.
What do you get 250? Oh,
Well-
I say, well, no, it's increasing. So this is an annual, and to date it, this was maybe done maybe 10, 15 years ago. I'm just going to guess a number out there, but this was done in the early 2000s, this calculation. Okay. So this number is decreasing if we go back in time, obviously, and increasing as we go forward. All right?
Okay.
So this is not linear. Again, it's not linear. It's not just 4 per year. It's increasing. So the previous year was 3.99. The previous year was 3.98, etc. And so going forward is 4.10, 4.11, 4.12, 4.13. You know, it's non-linear. It's an increase because it's accumulating. In other words, nature is still doing what it's doing.
Okay.
Mm-hmm. Yeah.
Okay,
That-
thank you.
Thank you for the question, because it's relevant. This number is not just static per year, but it's actually increasing as we move forward in time. And that's why the urgency to try to find alternatives to fossil fuels, alternatives so that we leave the fossil fuel sunk in the fossil pool, we leave it sunk underneath and don't earth it out, because this took thousands of years to make that and to sink that carbon that is under the earth. All right. But there's also creativity that could use some of this, as long as we filter out the CO2 and resync that CO2. So imagine hypothetically, if ever we came up with a technology to be able to trap this 9 gigatons of CO2 from industry and resync it, right, with machinery, that would be sweet, because then we can continue with our industrialization, continue burning fossil fuels, but we have sunk the CO2 that was being produced by industrialization. And that's the big challenge. Okay. All right, I'm going to leave it here for the slide, going into human trash and recycling. So see you at 11:30, okay? Got about 10 to 12 minutes, 11:30. Let me pause for a moment. Recording. All right, and here's the PowerPoint. So, welcome back. Any questions or comments from the cycles in nature? All right, I don't expect any luxury of detail that I give you. You know, as you have noticed now, my pattern with the lectures is that I tend to expand. Think of it as a gas laws, right? Gas with heat expands. So as I get heated into the lectures, I tend to expand. But in your summaries, you have to go in the opposite direction. You have to contract, all right? So cool down the lecture into a more compact form for the, and so really the challenge in the summary is to highlight just the essentials or the key points, even if it's just bullet points on the outlines that I provide to you. All right, moving forward now to human trash. I've mentioned several times already that we are the only species that really produces artifacts, and therefore stuff that stays behind even when we die. Because even when we're put into a coffin, eventually that coffin is going to break down and the bones will be, well, the flesh will be eaten away, and the bones can remain for centuries and even millennia, but all that eventually tends to break down. But that's not the major concern of our contamination of the earth, right? Is rather the artifacts that we leave behind, the artifacts, okay? For example, look at this shoreline. It's just amazing. And this was not put there for the photograph, okay, folks? This is a natural shoreline that has been invaded mostly by floating stuff in the ebb and flow of the tide. And it's just amazing because, for example, if this is a nesting ground for sea turtles, how is the mom sea turtle going to get through all this to lay her eggs? And then how is the baby sea turtle going to get back to the ocean through this stuff? Okay, that's just one example. Anyway, so here's a garbage dump, one of these huge mountain fills, garbage fills, right, that is filling up with a container of stuff that we have produced one way or another. This photo down here with the cars on the lower right, as dramatic as that looks, this crunched up cars, 3 years old or later, it's actually the least worried because this can be essentially melted down or grinded down, mostly to metal, which can be recycled, okay? So this one is the least of our worries. The most of our worries is this other one, behind this child with a t-shirt from Hard Rock. I'm sure this kid doesn't even have a clue what Hard Rock Cafe is or Hard Rock gambling is. But anyway, behind him is this mountain of electronic trash. All right, and this is a photo somewhere in Africa. And what happens is we ship our electronic trash to African countries that actually buy the trash from us. And then these children go into these mountains of trash and little by little start taking these things apart and pulling out a little tiny bit of gold or platinum or whatever metal is in there or anything, or copper that can be salvaged and sold. All right. Now, this is very toxic. This is very toxic, especially when it mixes with the sunshine that is breaking down these components and the rain that is seeping it into the soil, and their entire cities that live around these garbage heaps, and they live on from, they actually carve out sustenance from these garbage heaps, okay? Many countries in the Southern Hemisphere around the garbage, whether it be garbage like this, the classic traditional garbage from the kitchen or from industrial garbage, there are actual towns, entire cities that live around these garbage heaps, all right? So talk about an ethical issue. We'll get into that. I want to start from the oceans again, because the oceans is the largest surface of the earth, and the oceans is literally what's keeping the earth alive due to the cycles that I mentioned, prominently the water cycle that is keeping the earth green as we see it. These are actual photographs. This is a photograph. This is a satellite photograph. So this is pretty much showing you the different biomes of the world, right? And the big brown area here of the Sahara, the two lungs of the earth, the tropical rainforest of the Amazon basin and the Congo basin over here. And then the northern taiga or tundra, which even though is significant in land mass, is not that significant in forestation, in vegetation. And notice the color is not a deep green like the two lungs of the earth and the tropical region, but rather a brownish green, because that's tundra. And remember, tundra is mostly just mosses and lichens that grow on the surface of the earth, but no big trees or shrubs, right? Because of permafrost. Permafrost is the ground that is frozen underneath, and therefore, so solid water, and therefore deep roots are not able to take hold and penetrate there. So there are no shrubs or trees up there. This big swath, which is a huge chunk of Canada, and then some of Northern Europe, but especially Siberia, which is this whole swath here. Okay, but there are huge coniferous forests here. It's also known as a taiga or taiga, coniferous forest, pine forest, evergreens here. And then when you go further down, you get into the deciduous forest, mostly the US and Mesoamerica, which includes Mexico and some of the Caribbean, and then Europe and the East, right? Southeast Asia. Anyway, moving forward, I want to talk about the gyres, the 5 gyres that I had introduced to you earlier. Here's one little video. So I have a bunch of videos now for the second part of the lecture. Oh, come on. Oh, good. All right. I need to go here. Hold it. We need to make this optimized for video. Okay, so I have a number of little videos on this second half. This one is on the garbage trash, and this is done by the what's the name of this outfit? The Ocean Cleanup, all right? The Ocean Cleanup is one of the major companies that is trying to recycle and make and clean up the oceans, especially these gyres, the patches, the garbage patches. This is on the North Pacific, the Great Pacific Garbage Patch.
Pollution is one of the biggest threats the ocean.
There.
Plastic pollution is one of the biggest threats the oceans face today. But how much do we really know about it? On its mission to solve this problem, the Ocean Cleanup just published the most advanced research ever on the Great Pacific Garbage Patch, the largest accumulation zone of ocean plastic on the planet. Scientists have been studying this.
Sorry, because you may said he's talking about plastic specifically. He's concentrating on, oh, sorry, I should have done this. Let me back out for a moment because my enthusiasm, I forgot to mention the main thing about this is that there are 5 types. There are 5 types of man-made trash, all right? Wood, metal, glass, plastic, and electronic parts. Sorry, I got carried away. So these 5 ones, of the 5, they involve different types of recycling. And frankly, the wood is the easiest to recycle, metals, bless you, and glass. These 3 are basically the easiest to recycle, wood, metal, and glass. Then plastic depends on what kind of plastic, because there's a big difference between a plastic bag and a plastic bottle for recycling purposes. And then finally, the electronic parts are the most difficult to recycle or the least cost effective, where it takes actually money to recycle them. So it's not profitable, all right? Whereas the first 3 pretty much are profitable, but this also involves separating the trash, which is labor intensive or machine intensive, okay? So the 5 categories, the ones that are easiest to recycle so far and actually make a profit out of it, for example, recycle wood into paper or cardboard, which can be sold, right? Metal, obviously, for making machinery of all kinds. Glass, again, for making bottles and plate glass, et cetera, of all kinds. Plastic can also be recycled, but it's more difficult depending on the type of plastic. And then the electronic parts takes actually a lot of human labor to break it apart into recyclable parts. Okay. All right, sorry about that. Back to the little video. The Ocean Cleanup, trying to recycle. They're focusing mostly on plastic floating on the
area since the 1970s, mostly by dragging a small sampling net through the ocean. The Ocean's Cleanup's researchers believe this method was valid only for small debris and covered too small an area to reliably measure larger debris. So, in the summer of 2015, the Ocean Cleanup launched the Mega Expedition, crossing the patch with 30 boats simultaneously. In addition to using many small nets, 2 giant trawls were towed behind the fleet's mothership. In total, they brought back 1.2 million plastic samples. All were hand-counted, identified, and classified by type and size. A monumental task, taking a team of lab technicians 2 years to complete. However, the largest debris appeared less frequent and more scattered. Quantifying the debris required an area 20 times larger than the Mega Expedition to be covered, something only possible from the sky. The Ocean Cleanup ran the first ever aerial surveys of a garbage patch by converting a former military aircraft into a high-tech research platform. Cutting-edge sensors allowed them to reconstruct the 3D shapes of large debris to calculate their mass. The results of all this work? The Great Pacific Garbage Patch measures 1.6 million square kilometers. That is 3 times the size of France. The patch contains 1.8 trillion pieces of plastic, which equals 250 pieces for every human in the world. The total mass amounts to 80,000 tons, 4 to 16 times more than previous estimates. 92% of this mass is made up of the larger objects, all of which are destined to fragment into dangerous microplastics over the next few decades, if left under the effect of sun and waves. And because the findings show that pollution in the patch is increasing exponentially, the plastic is unlikely to go away by itself. These results paint a new picture of the problem and provide a baseline for the cleanup of the Great Pacific Garbage Patch, set to start in 2018.
Okay, so a lot of high tech here. You notice it kind of three phases. The first phase was very preliminary, run a single ship with a trolling net behind it. All right, that just gave a very, very tiny sample of what's going on because of the huge area. The second phase was to run those 30 ships parallel through a broader area, wider area. But again, those nets could only pick up smaller fragments. The big ones were not picked up on the net. So to quantify it and qualify it, in other words, see what kind of plastic stuff is out there, then they did that third phase of the airplane, doing a topography essentially of the surface. But this is only the surface also. Now, the danger is that gradually, naturally, on a combination between sunlight, especially ultraviolet, and heat and ocean waves and currents and tides, that the surface waves, is that the plastic is being broken down naturally into smaller and smaller fragments into what is known as microplastics. Okay, microplastics in general, very tiny, barely can barely see them by the naked eye, looks like a grain of sand, and then from there down into the molecular level, which we cannot see, but certainly the smaller they get, the more they get into the food chain and the food web of the oceans, right? And then that starts getting more dangerous for the human.
Sir,
So
Can I ask you a question?
Yep.
How long does it take from the surface to that broken down? It's in time.
Yeah.
Thousands of years or decades or months?
The time scale varies a lot. Okay, so the very short answer to that is I really don't know. When you think about it, you have to go basically plastic by plastic, right? How they isolated in that video. Let's see if I can do that. How they isolated in the video and quantified and qualified the various amounts, how they come up with this huge pile here, right? A slide, let's see. Somewhere, here we go.
The largest debris appeared less
Yeah. If we look at this one.
frequent and more scattered. Quantifying the debris required an area 20 times larger than the mega expedition to be covered, something only possible from the sky.
Okay, sorry, it's a little before this. It's interesting how we can go back on this one. Here we go. Yeah, okay, so you see on this slide how they have numbered each piece individually. He said about 2 million pieces, right? This came up from the trolling. And these are the small fragments that got caught into the trolling because the bigger things that were floating around did not get into those nets. They number each one and then they classify according to the composition of the material into different categories.
Task, taking
See, they put it into, this is a yellow category.
a team of lab technicians
This is the blue category, just these are different types of plastics, right? Classifying them like this, and then trying to determine all the different components, different types. And this is also to get a feel for which are the most abundant microplastics and so forth, okay? And then that can be traced back also into which are the most offensive plastics, actual plastics on Earth that are making this composition. One intuition could be, for example, water bottles, single-use plastic water bottles. How many millions of these water bottles are around in the world today? And most people, they drink once and they throw it away, right? So that plastic eventually breaks down, and it takes an X amount of time, which I don't know. It could be a few years, it could be a few decades, it could be centuries or millennia. And also it's a very dynamic system, because when you think about it, let's think of a plastic bottle floating in the ocean. Floating on the surface. Plastic bottle floating. What you'll see is that these bottles, there's plenty of them all over the place. Okay, but want to point out, at some point they get encrusted. These are all recent bottles. Want to find an old bottle that is encrusted with animals, mostly barnacle. Interesting, they're not giving. These are, I can tell you that these are mostly recent bottles because with a short period of time, they get encrusted here, finally. See, with barnacles, because it's a foothold. And these barnacles are piercing into the bottle. At some point, they'll break through the bottle, and whatever air was trapped there will be lost, and then the bottle starts sinking. Okay, as it sinks, the barnacles are going to get off or die, because the barnacles feed from the phytoplankton and the photoplankton on the surface. So it's a very dynamic system, okay, but it's long term. It takes a while. It takes a while for these bottles to break down, or it could be plastic. Oh my goodness, here's an actual chicken inside a bottle or a dead bird inside a plastic bag. You can imagine, I mean, the scenarios are myriad, right? Myriad. They get trapped, they get entangled with lines and nets and nylon fishing line, etc. So it's really difficult to untangle this and make some sense out of it, or even worse, to try to recycle this. That's the challenge. That's the big challenge.
I have another question. I'm
Yes.
sorry, but how does this trash in that huge amount have gotten into the ocean because of the accumulation of that in the trash locations, then finally goes to the ocean?
Sooner
Or
or later, it runs off into the ocean. Some people actually dump into the ocean. In many countries of the world, many cities are along the coastline, all right? Coastline cities throughout the world, especially in developing countries, and they just dump into the ocean, or they dump into lakes or dump into rivers, and the rivers run into oceans. So we are kind of in a bubble here in the United States, because the United States and Europe have a lot of regulation, and industry and individuals are fined and so forth, and we don't contaminate that much in comparison to other parts of the world. But we still do contaminate somewhat. I mean, I can tell you right now, there is raw sewage coming out into Biscayne Bay. All right, and Biscayne Bay is also a big tourist area. It's a big entertainment area where people go with boats. I've been boating there. I've been sailing in Biscayne Bay. I swim in Biscayne Bay. I snorkel in Biscayne Bay, and there's raw sewage coming out. And this is in Miami, USA, where we have the highest technology available with all the fines. So how is raw sewage going into Biscayne Bay? If this can happen in here, imagine what can happen in other countries of the world, right? So that's why I say it is a corruption thing. It's very challenging, but it's real. And this has been accumulating. And then the gyres tend to concentrate it because it's a vortex. It goes around and around and around, and the gyre goes through the coast and picks up whatever is on the coast and starts gyrating it, rotating it, and it tends to concentrate on the circle. Just like when we stir our coffee, we drop a little plastic, microplastic into our coffee, it's going to go to the center when we're stirring the coffee, right? Got to go to the center. So that's how these garbage patches are forming. Okay, so I want to zoom in a little bit more into microplastics and break them down into two main categories of the microbeads and the microfibers. All right, which microbeads can still be seen, but barely. That's the limit of our vision, of our unaided vision. But microfibers then are less than 1.1 millimeter. A millimeter is more or less the thickness of our nail. All right, that's about a millimeter. So 1/10 of that, we can no longer see it with the naked eye, but they're there in an increasing amount, in a huge amount, these microfibers. And these are the most dangerous ones as far as we can tell. So let's take a look first at microplastics and how it's broken down. And then this one is a little longer, of a scientist who did exhaustive research to find out the source of these microfibers. So Christina, these videos are going to trace it back to the origin. Here we go. There's going to be an ad. Hold on. Let me go here and let me see if I have
It was completely legal.
Oh yeah, okay. No, this one, no ad. Here we go. Oh, sorry.
90s. That plastic is still there because plastic
All right.
lasts out there for
Let me go back. Okay, so this is just scientists explaining kind of the origin of plastics in the oceans.
It was completely legal to dump plastic in the ocean until the 90s. And a lot of that plastic is still there because plastic.
Again, it's a little fast. She's saying it was legal up until the 90s to dump plastic and to dump anything into the ocean that wasn't officially toxic, like paint or something like that, okay? So non-toxic waste was even legal to dump into the oceans into the 90s, is what she said at the very beginning.
Plastic lasts out there for a very long time. It just breaks down into smaller and smaller pieces. We know that over 300 species of wildlife have ingested this material. It's been reported in animals. And so as it is eaten by animals, it actually can move up the food web. And as the
Sorry, this is worth seeing. This is a seagull or a seabird. There's the beak of the bird. All right, died. This is the carcass. You can see some ribs here. The bird died on the shore somewhere. And this is what's left of the carcass. It's everything that the bird has ingested. Bottle caps in particular, because they're shiny color and they're attractive to the bird, and the seabird goes down and gulps it down. Even a lighter, look at this lighter. Okay, so that's the stomach, the gut of the carcass of a seabird.
web. And as the scientific literature on this issue increases, literally almost every habitat they've gone to, seamounts, Arctic ice, coral reefs, deep sea, it's become ubiquitous. And I don't think anybody would fight anyone on an argument that plastic debris has not become a contaminant of concern.
We're collecting the samples by using a manta trawl. It's basically a big metal box with wings. It looks like a manta ray with a very long, about 12-foot mesh net off the back.
1, 2, 3, splash!
And at the end is a piece we can take off that has collected all of the solids. We rinse it all out, filter it through another strainer, and then put it into a jar. It's caught a lot of other stuff. If you want to take a look at what we're rinsing out of the screen, it's more tiny plastic.
What we're concerned about ultimately is what are the implications of trash going into the water, getting into the food we harvest? And we're still connecting the dots there a bit. We know that lots of trash goes out into the water. We know that the sun and waves breaks it down into small pieces. We know that many, many, many species of animals eat it. And we also know that bigger animals eat smaller animals. And we also know that we eat those big trophy fish. And so what we're really trying to figure out is how big a vector plastic is for transporting chemicals into the tissues of the animals that we eat every day. That's a big problem, much bigger than big chunks floating out into the ocean.
We don't know exactly what that plastic is. We don't know where exactly it's coming from. And if we're trying to find policy and educational solutions to it, we need to know what we're targeting. We can't just ban plastic. That's not going to work. What kind of plastic is it, and what's the best policy route to reduce it? Is it a ban? Is it a fee? Is it market change? Is it education and behavior change work? What's the best way to tackle it? And until we know exactly what we're dealing with, we're not going to be able to design the right programs to address it.
And Chesapeake Bay, by the way, notice it's an area of high density all around it, right? It's emptying out from Washington, DC and Virginia, that whole region. So it's an area of high urban density. I'm going to show you later another project that has been done there on the Delaware that is helping collecting the bigger chunks on the surface, the bigger chunks of trash. All right, so this little video leaves off on the issue of microplastics, which are microscopic, right, or barely visible by the human eye, and more specifically, what is known as microfibers. And then this other one, it's a little longer, like I say, it's a scientist who traces the origin. You're going to be amazed and surprised. And what's the major origin of the microfibers, which are microscopic and getting into the food web. And we are the top carnivore on the food web, right? Okay, let's see if there are any ads here. There may be some ads. So let me do this first. There's the ad. 210. Okay.
There's been a lot of attention lately on the tiny additives in our shower products. It seems, without many of us realising, they've been stuffed full of plastics.
They've designed to make things a little bit rougher and to get a better clean, but a lot of the products that they're used in go straight down the sink and then out into our lakes and rivers and ocean.
Again, what she said at the very beginning is the additives in our soap and gels and stuff like that. And the little tiny plastic beads for kind of doing like a gentle sandpaper on our skin, right? To get off dead skin. But they're tiny plastic beads that have been added to the soap.
Called microbeads, these tiny plastics have been causing so much alarm that supermarkets are in the process of banning the bead from their shelves. But in the stomachs of our seafood, researchers are mostly finding a different kind of microplastic.
Major thing that we were finding were these fibres, and so that really begged the question, where do they come from?
They're going down our household drains at an astonishing rate, but barely anyone seems to realise.
If animals that we're eating are eating plastic, we could potentially make that assumption that these chemicals are in our seafood.
What kind of microplastics are ending up in our marine life, and how much damage can they actually do? When I decided to take a closer look at microbeads, I didn't realise just how close I was going to have to look.
They're so small, aren't they, these tiny little beads?
Oh, they're tiny. We're getting sizes right the way from 1 millimetre all the way down to several micrometers, if not smaller.
The man helping me filter these rinse-off cosmetics is ecologist Dr. Mark Brown. He's been consumed with the problem of microplastics in the oceans for more than a decade.
It is a huge problem. So if you look at the amount of plastic in the environment, over 85% of that is microplastic.
The problem with microbeads is they're so small you need a filter paper to catch them. They're too small for our water treatment systems, but small enough to be easily ingested.
Over recent years, the amount of research has increased, and we've started to show that they're persistent, bioaccumulative and toxic.
3 years ago in the US, scientists trawling for microplastics in the Great Lakes found concentrations as high as 400,000 particles per square kilometre. They were amazed by how many tiny spherical beads they found in the mix.
It isn't just microbeads, it's much larger bits of plastic breaking down into the same micrometer-sized fragments. And so we're really concerned as to whether or not these particles could be accumulating in humans and wildlife.
The evidence shows they are, even at the very base of the food chain. Zooplankton, for example, are a major source of food for fish, whales and seabirds. These were filmed under a microscope in just one drop of water. Normally, they draw algae towards their mouth by creating currents with their legs. But when tiny fluorescent particles of polystyrene are added to the water, they eat those instead. Microplastic is now regularly being found in wild-caught zooplankton in the North Pacific. Just through eating these tiny crustaceans, salmon are thought to be consuming around 90 particles of plastic a day.
So these particles look so small that if you swallowed them, it doesn't look like they'd do much harm. I mean, don't they just sort of pass right out the other side?
Well, this is what we thought until we started doing experiments whereby we were actually feeding these types of particles to them. We were astounded by actually what we found.
I'm much more disturbed by what Mark shows me next.
So we know that invertebrates, in particular mussels, are exposed to microplastics in the environment. What we really wanted to find out is whether or not these tiny particles of plastic get any further than the stomach itself. So we exposed these mussels to tiny particles of polystyrene, and we then tracked these particles in the tissues of the mussel itself.
This footage, captured by marine scientists at the University of Connecticut, shows how tiny bits of plastic are drawn into the mussel and along the gill filaments. They get trapped here just like food particles and pass down the ventral groove into the mussel's mouth. But no one knew they could penetrate the gut barrier until Mark took samples of the mussel's blood. When the blood is analysed days later under a special infrared microscope, the molecular vibrations of plastic can clearly be identified.
And here you see right in the middle of the actual slide there is the polystyrene bead.
So that means that the plastic has made it from the stomach of the mussel into the circulation?
It has, yes.
That's astonishing. So how long have you seen the particle remain in the circulation?
They've lasted in the actual mussel for 4 months. But more disturbingly, as these particles of plastic get smaller, which is what they'll likely do through the breakdown in the environment, the rates of transfer actually increase massively. The concerns that we have really is that it can cause inflammatory responses, so the body of the mussel itself recognises it as a foreign particle and starts attacking that. Because the particle can't go anywhere, you get scar tissue forming around that.
But the reaction to a foreign body in the tissues is just one of the side effects.
What's most concerning researchers is not just the physical damage caused by microplastics when they're ingested, it's the toxic load from the chemicals they carry.
One of those researchers is Dr. Chelsea Rockman from the University of California.
I'm an ecotoxicologist, so I look at the fate and effect of chemicals and plastic debris in our environment. Plastic is kind of like a little sponge for a lot of the chemicals that are already out there, the pesticides, the flame retardants, industrial chemicals, etc. Plastic concentrates, hyperconcentrates these chemicals at very large concentrations, sometimes 1 million times what we find in the water column. So PCBs, which were banned in the early 80s, DDT, which was banned in the early 70s. And I find these on every single piece of plastic I take out of the ocean. Metals like copper, lead, nickel, cadmium.
Plastic also contains unique chemical additives of its own from the manufacturing process, such as flame retardants and antimicrobials.
So the big question there was, do these chemicals associated with plastic debris end up in animals when they eat them? So basically, we set up a study in the lab where we fed fish plastic that had these chemicals associated with them. We fed them environmentally relevant levels.
Dr. Rockman exposed Japanese Medaka to plastic particles that had been pre-soaked for 3 months in San Diego Bay. After just 2 months, higher levels of what's known as PBTs, or persistent bioaccumulative and toxic chemicals, were measured in the flesh of the fish, particularly flame retardants unique to the plastic.
So a lot of these chemicals are fat-loving and water-hating. But once they've transferred from the water into that fat phase, so the fat in a fish, they're incredibly persistent. I might have, a mechanism in my liver to take that PCB and break it down into a safer form. But once my liver is overtaxed, it might have a hard time doing that, and I'm going to start storing those chemicals in my body.
Chelsea predicted signs of damage would first be seen in the liver. Here she observed cell death and excess fat, a sign of liver overload. One fish.
Remember, the liver is the one that is filtering toxins from circulatory system, the rest of the body. That's why the liver may be the one that gets it first, but the liver is a vital organ, as you know. So when it's overtaxed, then it could lead to cirrhosis or some other damage.
Fish even developed a liver tumor.
And when we've taken fish in the lab and fed them the virgin plastic that doesn't have this mixture of things from the environment, we see less of an effect in the fish. So this mixture is having an effect.
Even at very low concentrations, flame retardants are known to cause endocrine disruption, an effect observed in the fish.
But endocrine disruption is a disruption in the hormone system, which is what controls reproduction. So if that's not functioning, some people joke, if you don't reproduce, what are you here for? So it's a very important system.
Dr. Mark Brown also found chemicals transferred from the plastics to lugworms, a common marine sediment dweller.
We saw reductions in survival, reductions in immune function, and we saw a reduction in their ability to feed and process sediment. Things like triclosan, which is sort of an antimicrobial, is added to plastics, and that was one of the major killers of the worms.
Worms that process sediment are crucial for the survival of a complex food web of organisms.
And so when you remove these worms from the environment, you see a complete reduction in the numbers of animals and plants that can actually live on that shoreline.
These studies raise the important question: if chemicals can transfer from plastic to marine life, how much of our seafood is eating plastic?
I got it. It's huge though. Ah.
They're in Australia.
Well, maybe it's huge. Let's see.
Here in Sydney Harbour, we're out catching some of the state's most popular eating fish.
Oh,
or at least trying to.
In the harbor.
huge. This is called a tiddler.
That's not what you're after, is it? Oh.
We've looked right the way throughout Sydney Harbour, which is a really big harbour, and we found a surprisingly high concentration of microplastics in the sediments, and up to 60 per 100 mils of sediment. That's a really high concentration.
So is that why you think you'll find plastic in the fish?
Yeah, so because we did find high concentrations in the sediments, the first thing we wanted to do was to see which species it was getting into, if any, and so we targeted the fish that were feeding on the sediment. And this is a mullet. This is really a target fish for us. And these guts in here are full of sediments.
So this is a popular eating fish?
It is popular. It's not quite as tasty as the bream. It depends on your taste. These bream are really tasty, so these are really targeted by the recreational fishers.
We're taking these fish back to the Sydney Institute of Marine Science, where researcher Jen Halstead has been looking through their guts for any traces of plastic. Her studies have revealed that 30% of the mullet and 13% of the bream have plastic in their guts. But typically, it's not coming from face scrubs or shower gels.
So I've just found something that looks suspiciously like a plastic. Do you want to take a look?
Yep. Doesn't really look like a microbead at all.
Yeah, well, actually, most of the microplastics that we're finding are in these forms of fibres, so that looks a lot like what we've been finding.
So is that a plastic fibre?
Yeah, well, we actually don't know at this stage. It could be synthetic, it could be natural. That's why we need to take under further investigation.
These results mirror a study 2 years ago by Dr. Chelsea Rockman, who looked inside the guts of fish from both Indonesia and the US.
I'm collecting fish from local fishermen that are selling them for human consumption, either out of a local market, straight off the dock, as you see here, or it's actually going through Pillar Point Fisheries over here, which then gets shipped.
Back in the lab, Chelsea discovered around a quarter of the fish from each country had debris in their guts, but the type of plastic differed.
So what you see back here is a really good example of a piece of plastic taken from a fish in Indonesia. So this is from a silverside, which is a planktivorous fish, actually about this big. And what's a little bit disturbing about this one, actually, is that people eat the entire fish. And this is an example of where this plastic actually would go to, be transferred to a human.
In Indonesian fish, all of the debris was microplastics from larger, broken down pieces. But in the US, Chelsea mostly found microfibers.
But if you look closely at this, you can see like the actual, nylon intertwine. That does not look natural, plant-like.
Chelsea didn't pinpoint the source of the fibers, but with the help of vibrational spectroscopists at Sydney University, Dr. Mark Brown has followed the trail further.
The forensic techniques that we use shine an infrared beam or laser onto the sample. And we use that absorbance and reflection of light to tell us the type of polymer that we're actually finding there.
The vibrational fingerprints of fibers found in Sydney fish do indeed match plastic, but from a source that to me was totally surprising.
When we match this to a database of polymers, it clearly identifies this one as nylon. The second one here matches to polyester, polymers used in clothing. They seem to have a high fiber diet and it's full of synthetic fibers. They certainly seem to be the same types of fibers, same physical structure, the same colors.
With the mullet, we caught 30% of them had a microplastic particle, at least one, in their gut at the time that they were caught. If you model that, it actually means that pretty much every mullet is eating at least one microplastic particle every 3 or 4 days.
I'm amazed, but Mark has suspected it all along. He's looked at multiple shorelines on 6 different continents, and in each case, fibers were the dominant microplastic.
We expected to find lots of small particles from either from the facial cleansers or from, larger bits of plastic that had broken down. But the major thing that we were finding were these fibers. What was peculiar about what we were actually finding was the proportions actually matched the types of polymers used in the textile industry, not only in terms of the types of fibers, but also in the numbers.
The closer they were to sewage outfalls, the higher the concentration of fibers.
And we found exactly the same types of fibers, acrylic, nylon, polyester, being emitted from these sewage treatment works.
The simple answer seemed to be that fibers were escaping from washing machines.
So most of the fibers that we're finding in the environment were polyester, so we essentially chose some garments that are made out of polyester, things like fleeces, which are the poster child for sustainability because a lot of bottles get recycled into them. And we essentially put those into washing machines separately, and we counted the number of fibers that were coming off.
You probably haven't thought that much about the proportion of clothes we wear that are plastic. But today, around 2/3 of the clothes we buy are made of synthetic fibers.
The so-called eco-fleece sheds almost 2,000 plastic fibers each wash. Other polyester garments aren't much better.
They release similar quantities into the environment. It doesn't seem just to be one type of garment. They all seem to be doing it.
But can these thin fibers carry the same chemical load as the other more spherical plastics tested?
I think the toxicity of the microplastic particles will vary with their shape and size. So the fibres have an incredible amount of surface area. The more surface area, the more likely they are to actually carry those other contaminants, and they would then be transferring into the fish tissue.
Aside from the direct effects of eating plastic, chemical doses are already known to biomagnify up the food chain.
These chemicals might absorb to the plankton at the bottom of the food chain, and one fish eats 10 of those plankton. Now that fish has a larger dose, right? 10 times the dose of the plankton. And then several of those are eaten by a larger fish. And so the question is, how is plastic contributing to this thing where we're seeing these large concentrations of chemicals in top predators?
One of those top predators is us, and it's well established that toxic chemicals can transfer from contaminated fish to humans with serious side effects. With all the billions of people wearing plastic clothes, suddenly the problem appears a lot more diabolical than microbeads.
We've been speaking to the public, government and industry. The public have voted this one of the most important issues to be sort of tackling. We've spoken to the government about it, yet they seem to be focusing on other activities, things like microbeads and also packaging. When we have gone to talk to clothing companies or appliance manufacturers for washing machines, the appliance industry and the clothing industry haven't been helpful.
Mark says a simple filter could be added to washing machines to stop all kinds of toxic fibres from reaching our seafood. And do we really need all the industrial chemicals added to our clothes and other plastics?
We're seeing all sorts of chemicals come on the market, up to about 15,000 per day. The problem is that we're not doing the tests to keep up with the types of impacts that could be occurring. Which one's causing the impact and which one's is causing more of a worse impact? If we understand that, we can start making choices.
We need a healthy ocean because it is all connected, and our fate.
So this one was a little longer, but you see, he gets right down to the nitty-gritty of the most dangerous one, which is these microfibers, right? Because of their increased surface area, many times over, and they are traced back to clothing, to synthetic clothing that we use. And who doesn't use clothing, right? So it's a very, very big challenge that we have ahead of us, but at least now one major source of the microfibers has been identified. And then let's see where we go forward. He's suggesting a simple solution as that filter that can be put on the dishwasher, for example, or the affluent. Of course, we'd have to do that at the individual basis in each home, or perhaps the machine itself, when it's sold, the dishwasher on the effluent, on the exhaust pipe, could have this filter already integrated. Anyway, it's one thing out there. And I think the evidence is pretty clear that these microfibers do get into the tissue of the fish. And sooner or later, we are consuming that fish or consuming an animal that's consumed the fish. So it's a cause for concern. We only have about a few more minutes left. Let's see. I'm just going to select one or two from here that will help. You can look at these on your own, but one that I wanted to show you, these two, single stream recycling, because it involves what happens with our trash. I still remember the time when we had to separate plastic from the newspaper, from the glass bottles and the wood pieces and all that, and metal. Now this is called single stream.
Waste management is.
So this shows how single stream recycling is then separated, but you can see that it's labor and machine intensive. And so they have to make it to at least break even, if not make a profit. Otherwise, if they're gonna lose on this, then it's not a workable
Is on a mission
plan.
to drive environmental performance with solutions that manage and minimize waste, recycle valuable resources, and create clean, renewable energy.
They say one man's trash is another man's treasure, and here at Waste Management, we really believe that that is true. We've really had a shift in our mindset where people historically used waste as trash. Now we really view waste as a resource, and it's a material that we need to manage and find innovative uses for.
Waste Management is North America's largest residential recycler, recovering and processing over 8.5 million tons of plastic, paper, glass, organics, e-waste, and metal per year. By the year 2020, our goal is to nearly triple the amount of recyclable materials we manage to more than 20 million tons per year.
We are aggressively investing in new single-stream technology as well as building new single-stream recycling facilities like the Philadelphia Material Recovery Facility. And when we build these plants, we're constantly looking at the newest and latest technology to extract more value out of the materials that we manage. So whereas in the past, there might have been some grades of plastic, say, that we couldn't capture, now at this facility, we're capturing film plastic and we're capturing 1 through 7 plastics. Single-stream recycling really makes it much easier for the consumer or the user to do it on a daily basis. So whether you're a resident or at a commercial property, really all you need to do is put your paper, your plastic, your metal, glass, cans, all in one container, and our facilities will do all the work.
It's hard for me to come with any reasons why not to do single-stream recycling. The more people know about what we do, the better and the easier it's going to be to recycle. And that's the goal. Send it this way, and we'll take care of the rest.
By making recycling easier, single-stream systems can boost recycling participation rates by over 50% and make the recycling collection process simpler and more efficient for residents, municipalities, and commercial customers. The Philadelphia Material Recovery Facility in Northeast Philadelphia exemplifies our commitment to recovering the value in waste. The 60,000 square foot facility was constructed using sustainable building and design techniques, which meet the LEED Silver certification standards of the U.S. Green Building Council. This innovative single-stream facility can process and sort more than 20,000 tons of recyclable newspaper, cardboard, aluminum, glass, and plastic each month, equal to the weight of 261 Boeing 737s. Customers who purchase recycled materials want them to be free of contaminants. They don't want plastic or metal mixed in with their paper, or paper mixed in with the plastic they've ordered.
The expectation is that we should be close to 100% purity in the materials that we're sending to our customers. We expect our machine to give us 95% of the quality. The extra 5% we do manually. We have all this technology, but at the end, our employees make the difference.
So let's examine the single-stream separation process and how people and technology together produce a quality end product. A truck containing mixed recyclable materials arrives at the processing facility. After being weighed and recorded, the contents are emptied onto the tipping floor. The recyclables are loaded onto the main feed conveyor, which directs the material to several different sorting areas. In the first area, large rigid plastics, such as toys and buckets, are separated for baling and sale to plastic markets. Non-recyclable materials are discarded into the trash. The materials continue on to a series of disc screens. This specially designed separating equipment consists of rotating discs that push cardboard over the top. Larger pieces of cardboard are sent to a second conveyor for another pass to remove contaminants, and then to the baling process. Material that falls between the disc screens moves to the next sort area called the combination news screen, where paper materials are separated from household bottles and cans. The first section removes most of the newspaper, advertising inserts, and office paper, which is filtered onto a processing line, where any materials other than paper are manually removed. This product automatically falls into the final bunkers, which, when filled, is fed into the baler and prepared for customer pickup. The pre-sort and newspaper conveyor stations contain a series of air vacuums. These allow plastic bags to be removed from the line and sent to a separate bunker. The plastic bags, known as film plastic, are also baled and marketed for sale. After the disc screens have sorted out paper and cardboard, what's left, steel, glass, plastic, and aluminum, is directed to a glass breaker to remove glass, and then to a paper magnet to remove any remaining paper and film plastic from the container stream. The glass is transferred by conveyor to an inside storage bunker. The containers exiting the glass breaker then pass under a magnet that removes all steel cans for baling. The remaining materials, primarily plastic containers and aluminum cans, are then passed under an optical scanner to remove light plastic containers, such as soft drink bottles. The remaining containers pass a manual sort station where additional heavier plastics are captured. These include clear plastic containers such as milk and juice bottles, and colored containers such as liquid detergent containers. These products are also separated for baling. What's left, cardboard juice cartons or non-conforming plastics, pass under another optical scanner for removal. The remaining material goes through a magnetic field known as an eddy current to remove the aluminum, which is blown into a material storage bunker for baling. Any remaining material not repelled by the eddy current goes to the waste line for transfer to a landfill or a waste-to-energy facility. At Waste Management, we're constantly on a mission to extract more value from the materials we manage, and at the same time, improve the environment of the communities where we operate.
When you can go back home and tell your children that what you do, and they find it interesting, and not only that, you are actually influencing the future of the planet by doing what we do.
Yeah, well, one thing I got out of this one is that it's both labor intensive and technology intensive, right? Which translates into money for the industry. So they need to at least break even in the different products that they sell. Notice that they sell out then the plastic, the metal, the glass. They sell it out to other companies that will process it, reprocess it, mostly into containers. And that has to generate enough revenue to pay those workers and to also maintain the technology that is used. It's a major enterprise. It works mostly by volume. But the one advantage is that it's single stream. Single stream means that we put all of the synthetic stuff into one of those big green bins. It's not supposed to have organics in it, like food and stuff like that, all right? But that single stream is easier for us, for the consumer, because we just gotten too lazy to separate ourselves. I remember I go back last century, basically, it was still, we had to separate individual, and there would be a different truck that would pick up the newspaper, and a different truck would pick up the glass and so forth. But now that's too cumbersome, so the industry has to do it. And they have to somehow at least break even.
Father, how many of those facilities are really?
Not too many. This is kind of state of the art right now. They are typically in high density areas, high population areas, right? Like Philadelphia, the Northeast, the New England area is high density. But you know, it's all about scaling it up. If that works, then they can reproduce. In other words, the one that is more expensive to build is the first facility, right? If that works, they can figure out how much garbage they need, how much population density they need around that station to make it feasible, and then they can reproduce those plans, those blueprints in other parts of the nation, and that way make it effective little by little. And technology is also improving little by little, but I don't see any way we can get out of the labor component of it, right? Because it's the human eye that sees the difference very fast, and the human hand that reacts to that. So yeah, it's a work in progress, but at least they're working on it.
And here in Miami,
Right. You brought up
I heard
education.
that we're not recycling anymore.
Right. What's happening in Miami, from what I know, this is a conference I went to last year, maybe a couple of years ago already, it's associated with the Bay, and the county people were there, and Waste Management was there, and the officials, the government, local. Apparently what in Dade County, what is happening is that this system is not working well. Maybe they don't have, maybe I think the recycling facility is kind of outdated, and they haven't pumped enough money into it to make it like this state of the art and efficient. So for now, what I understand is that what we put in our recycling bins is packed up into huge trucks and sent to Broward County, and in Broward, it's burned. Okay, the trash is burned, and at that point, it doesn't matter if it has organics or not. In fact, the organics will actually make the burn go more intense and faster. And then that burning, they heat water with that, and they make steam, and the steam generates electricity with generators, all right? But CO2 is produced through the burning, and then you have the ash. The ash is taken to landfills or other places, mixed in with soil, can be used as landfill. And those are the big mountain landfills that you see going on the turnpike as you go north from Dade into Broward County, all right? That's my understanding what's happening. So the actual recycling is not happening very well here in Dade County for some reason. I think it's a question of providing resources to update these recycling plants to make
Money.
it comes down to money, and then when it comes down to money, it comes about, to votes, because this has to come out of the taxpayers somehow for the county to subsidize these the industry, right? If the industry doesn't make a profit out of it, then it's a problem. There's one, you can watch these on your own, but I want to show you this one on the positive side. I like to end up on this positive of what's been done in the harbor, Baltimore. This was a few years back, of this machine that traps garbage and makes traps floating stuff from Baltimore Bay.
I think there's a little bit of apprehension involved in trying new technologies, and a lot of people heard the idea and said, that's pretty off the wall. I don't know if that'll ever work. I used to walk across this bridge every day, and I would see the trash coming down the river, and I'd hear the tourists say, "Ugh, this harbor's disgusting." So I thought about it every day on my way to work, and this is the idea I came up with. And my partner Daniel and I enlisted his help to help put it together and put it in on May 8th.
So here we are on the Jones Falls in Baltimore's Inner Harbor on a rainy day, standing on the water wheel, and which is behind me here. You can see this is the water wheel. It's being turned by the current of the Jones Falls, which is flowing very rapidly because we just had a pretty large rainstorm. And that wheel is turning this conveyor belt that is picking up all of this trash that is flowing down the Jones Falls. You can see we've got a lot of plastic bottles.
All want clean water. They all want the ability to swim or recreate in water without coming into contact with trash or sewage or stormwater pollution. And you can see a lot of that, especially online. There's a lot of concepts out there for cleaning up trash in the ocean. And just those concepts become very, very popular on the internet. And part of the power of the water wheel is that it's here, it exists. People can actually see it operating every day and cleaning up the trash. John is a huge inspiration to, I think, a lot of people. Here's a guy who solved this problem of just trash in the waterway, something that, thousands of us have been looking at for a very long time. And, he actually had the ability to think about the problem and come up with this brilliant device.
As you can see, it moves kind of slowly, but slow and steady in this case is just fine.
We've captured over 3 million cigarette butts with the water wheel since we installed it. Second to that, I would say plastic bottles. We've probably captured about 50,000 plastic bottles since we installed it. And then styrofoam, basically anything that floats. It's completely sustainable in that it's powered by hydropower, and when there isn't enough current in the Jones Falls, we have solar panels which provide solar power to pumps that actually pump water onto the water wheel to keep it turning even when there's not enough current.
So I'm going to go ahead and turn it on.
Okay, so in other words, this water wheel, right, is powered by, it's a conveyor belt, and it's powered, it's autonomous. It's powered by hydraulics. In other words, the wheel itself turns as the river flows down, and the wheel turns, and as the wheel turns, it makes the conveyor belt go up, pick up the trash from the base of the conveyor into a container in the back, a bin, and then that bin is taken out for recycling. And when there's not enough flow in the river, right, and it's too low or too mild to move the conveyor, then the solar panels kick in as an auxiliary to run the wheel. And that's what he's doing now.
Make her go. The water's being pumped in 2 stages from the harbor up into this reservoir, and then from the reservoir up into the wheel. And so that's what's making the wheel go around today, because the river, we've had a dry spell and there's not much flow coming out of the river. Even on these dry days, we still get a fair amount of trash. It's like, you know, a couple trash cans full, but after a storm, we'll get as much as a couple dumpsters full. So the power from the wheel, the turning wheel, is transferred to the conveyor and to the rake system through a system of gears, chains, belts, pulleys. So it doesn't really care if there's a big 2,000-pound log on it or just a load of styrofoam. It just keeps on turning.
So here we are once again at the back of the water wheel, seeing what kind of trash is coming over the conveyor belt today.
I love hearing people talk on their cell phones and just be like, you wouldn't believe what they have here in Baltimore. You know, it's called a water wheel and it's like solar powered. And so hearing that excitement from everyone has just been terrific. Ultimately though, our goal is to actually put the water wheel out of business. We know that it's an end of pipe solution. It's great because it's immediate and it's innovative, but the real solution is that people need to change their behavior.
We've heard lots and lots of people say, oh, the harbor will never be clean. You can never get all the trash out of the harbor. I think, you know, we're not taking all the trash out of the harbor, but we've made one big dent, a noticeable dent that's noticed by everybody who uses the harbor, who boats on the harbor, who lives on the harbor, who jogs the promenade. We had one article that said this is the most promising technology for keeping the plastic trash out of the oceans. And, you know, we're hoping just to clean up this harbor right now. But I think we can take it to a bunch of different places and make it a valuable technology or a valuable asset to keeping the oceans clean, the rivers clean, the harbors clean. It's a dirty job, but it's a worthwhile project.
Okay. Anyway, that's a positive one. Just a couple of guys that put it together, and that can now be reproduced. In fact, you can go online and you see number of variations of the water wheel all over the place. You know, they have variations of it. Some are longer now that look like a tube, a huge, looks like almost like a train. They've made various designs, different designs out of it. So anyway, take a look at the other videos and some remediation that is happening here. Bioremediation is when a natural area is disturbed and it's contaminated or invaded with either trash or invasive species and so forth, how it's being cleaned up and restored to its original beauty and its original intention, right? You can look at all these various little videos that are here. They're short, they're typically 3-4 minutes each and so forth. This one in particular was an interview done by the Wall Street Journal, between the Tyson, which is the one that makes hot dogs and all kinds of food, right? Roundup food, meals, and Waste Management, how they partnered up to recycle some of the trash or some of the byproduct of the Tyson company. So take a look, and there are many, many more of these types of videos online that you can look at. But basically, the idea of trying to recycle these processes, again, the toughest one is the electronics, or what is known as e-garbage today. E-garbage is the term, precisely because of the complexity of these components and how it's so labor intensive to take them apart and make anything profitable out of them. Okay, we'll stop here with cycling and human recycling. Pick it up next time. We'll meet again next Saturday. Going forward, we'll start looking at more of the human population density and climate change. Any parting questions or comments? If not, we'll close it here.
Thank you, Father. Very interesting.
Okay, thanks again. Many blessings. Bye-bye.
Thank you, Father.
Okay, don't forget, watch those videos and also try to read that Aqua Fons Vitae, the document on water, right? As it takes more and more relevance as we go forward. Bye now. See you next week.
Thank you, Father.
Okay, thank you. Bye.